In this video, we're going to talk about intermolecular forces and their effects on physical properties such as boiling point, melting point, vapor pressure, density, viscosity, and surface tension. We've talked briefly before about intermolecular forces. At its most basic level, we distinguish between polar and non-polar molecules. That's not the only type of intermolecular force that exists. Dipoles are not the only kind of intermolecular forces that exist, but they are going to take up the most of our attention. Nevertheless, there are other kinds of what are so-called interparticle, not really intermolecular force, but interparticle attractions. Ionic bonds, for example, are due to electrostatic interactions. So I'm going to lump in electrostatics, even though technically these are not intermolecular because they're pulling two ions together. We're going to call these electrostatic interactions. We're going to lump them together as a type of intermolecular force. The attraction of positively and negatively charged particles, ions, atomic ions or molecular ions, the so-called polyatomic ions, their attraction to one another is based on electrostatics, meaning electrical charge, and the charge is unchanging, it's static. So positive and negative ions attracting to each other. These are the strongest by far. These are the strongest type of attractive force, bringing two particles together or two molecules together, two molecular ions together. The particle can be a molecule or a single atom or even just a fundamental particle such as a proton or electron. This is not technically an intermolecular force. Okay, so I already mentioned that. It's not technically intermolecular, but we're going to lump it in. It is the strongest type. And for that reason, whatever effects that intermolecular forces have on the physical properties of substances, these are going to have the strongest effect. They're going to have the highest boiling points, the highest melting points. They typically have the highest densities and other sorts of properties. So leaving behind the ionic compounds, let's look at molecules, neutral molecules, not polyatomic ions. Polyatomic ions are not defined by their molecular structure or their intermolecular forces. They are mainly just, polyatomic ions are molecules, but that all ceases to matter once they're charged. Here we're talking about neutral molecules. And of course, you know that there are two general types of molecules, covalent compounds. There are polar covalent compounds, polar molecules, and there are non-polar covalent compounds or non-polar molecules. Non-polar molecules still exhibit a certain level of polarity. Now, we've been calling them non-polar, but that's just sort of a naming convention or a labeling convention. The truth is, even the most non-polar molecule, like say, for example, dinitrogen or dioxygen, or methane, or any of the hydrocarbons we've talked about, even though we call them nonpolar, the truth is they have a small amount of intermolecular attractive force still inside of them. And this is due entirely to something called the London dispersion force. The London dispersion force. It's also known, by the way, AKA, as known as the van der Waals force, or also called the instantaneous dipole. Now, for the most part, I'm just going to refer to these as London dispersion. But you should know that there are other names for this exact same kind of force. Instantaneous dipole or temporary dipole, as opposed to the permanent dipole of polar molecules. These are called instantaneous or temporary dipoles. Van der Waals, well, you'll meet him again when we talk about a little bit about his equation for gases. No, wait, we already did. I think we already did talk about him. Never mind. The van der Waals equation, same guy. Okay, so even non-polar molecules have some kind of temporary dipole, and we're going to see what gives rise to that. Long story short, it's a non-uniform distribution of the electrons in the molecule, around all the atoms that make up the molecule, giving rise to temporary and very short-lived and very weak dipoles around the molecule. But even these weak forces, on average, can build up over a population of billions, quadrillions of molecules and atoms. So London dispersion force is polarity for non-polar molecules. London dispersion force is really only important for nonpolar molecules. All atoms and all molecules have London dispersion forces. It's simply not the major type of intermolecular force for molecules that have permanent dipoles. So if a molecule is a permanent dipole, you can almost ignore its London dispersion force because that's not going to be the most important feature of that molecule. Just as if a molecule has a negative or positive charge, then suddenly its intermolecular forces really aren't that important. The all-defining characteristic then becomes the charge, the positive or negative charge, and the magnitude of that charge. So there's a hierarchy of attractive forces. London dispersion is right near the bottom of that hierarchy. Then we have the dipole-dipole force. Dipole-dipole is what we've been calling the dipole. Whenever a molecule has a net dipole, it has the possibility of being attracted or attracting another molecule with a dipole as well. Dipoles attract one another. So the London dispersion force is a temporary dipole. That attracts other temporary dipoles and even permanent dipoles. But the dipole-dipole force is between two permanent dipoles, meaning it's built into the structure, meaning the way the atoms are assembled to each other, less electronegative elements are bonded directly to more electronegative elements, and that's just a feature of the molecule. That's the way it's put together, and those dipoles do not, of course, cancel each other out. If they cancel each other out, then you're back to London dispersion. You're back to a nonpolar molecule. So London dispersion is a dipole for nonpolar molecules. Dipole-dipole is the net dipole associated with polar molecules. However, there is an especially strong kind of dipole called hydrogen bonding. Hydrogen bonding is not a special, or it's not a distinct type of intermolecular force. It's just a dipole like any other dipole, except for the fact that it's extremely strong. And the reason it's so strong is because it involves the bonding of a relatively small and very relatively low electronegativity non-metal hydrogen bonded to any one of the three most electronegative elements on the periodic table: fluorine, oxygen, or nitrogen. If hydrogen is directly bonded to any one of these three elements as part of the structure of a molecule, then you have a special type of strong dipole-dipole called hydrogen bonding. It's so strong that it gets its own name, despite the fact that it's really just a subcategory of the dipole-dipole force. So hydrogen bonding is a special case, an especially strong case of dipole-dipole. And again, it's only with those three elements: fluorine, oxygen, or nitrogen, either a hydrogen-fluorine bond, which there can only be one molecule representing that. There are millions of hydrogen-oxygen bonds out there, or nitrogen-hydrogen bond, and there are, of course, millions of those as well out there in the world. And we'll take a look at some examples. So the hydrogen must be directly bonded. That's the only way you get the especially strong type of dipole, the relatively positive, partial positive charge on hydrogen, and the partial negative charge on either nitrogen or oxygen or fluorine. Remember, two electronegative elements an electronegative element bonded to a less electronegative element results in an uneven distribution of charge, or partial charge, we should say. These are not true positive or negative ones. These are fractions of charges. These are partial or slight charges on the atoms. These are not ions. I want to make that clear. These are not, though the underlying principle is, of course, one of electrostatics, meaning opposite charges due to electrons and protons fundamentally. These are partial charges. These are not full-on +1, -1, +2, -2, like you see in atomic ions or polyatomic ions. And then finally, we have something called the ion dipole force. Now look at that word. It consists of two things that normally aren't together: ions, which are usually just true ions, like atomic ions, like calcium with its +2 charge, sodium with its +1 charge, a true ion, and a dipole, which is part of a molecule. This involves a molecule interacting with an ionic compound, and that is the only situation in which you will see this. when you have the interaction between a molecule and an ionic compound. Well, where's the one place you see that? The only time you really see that is when you have a compound, a molecular compound, or excuse me, an ionic compound dissolving in the molecular compound known as water. In other words, if you see an ionic compound dissolving in water, the ionic compound provides the ions, the water provides the dipole. Remember, dipoles are associated with molecules, not with ionic compounds. Ionic compounds do not have dipoles. They do not. Ionic compounds are made up of ions, but they do not have dipoles. So a molecule has a dipole, and water especially has a strong dipole because it's all hydrogen bonding. So the dipoles from water interact with the ions from ionic compounds, and they cause that ionic compound to dissociate, to break up into its individual ions and spread out in the water. So the only time you encounter the ion dipole force is when you have ionic compounds in aqueous solution, dissolving in water. That is the one and only situation that the ion dipole force is going to apply in our example or in all our discussions. Technically, any polar solvent, any liquid polar substance can dissolve ionic compounds to a certain extent. But mostly we deal with aqueous solutions, meaning water-based solutions, where water is the solvent and what's being dissolved is usually an ionic compound. So that's the ion dipole force. We'll take a closer look at each one of these right now. Let's talk about the origin of the London dispersion force. So the London dispersion force, aka van der Waals, aka instantaneous dipole, the temporary dipole, whatever you want to call it. I'm going to call it the London dispersion force. What gives rise to this concept is a little bit different. It's not a permanent dipole. It arises out of the serendipitous, non-uniform distribution of electrons around either an atom or an entire molecule. Electrons have some freedom to move around atoms and molecules. Because of that, sometimes electrons will be evenly distributed around an atom, like in this first picture right here. The electrons, let's just take, for example, let's divide up an atom. This is a single atom. This right here is this circle, or this sphere, represents a single atom. It has, let's say it represents a helium atom, helium with only 2 electrons and 2 protons. Let's say at the beginning, the helium has 1 electron on each side. We divide the atom up into 2 even sides, or 2 hemispheres, and we have an electron on either side. So the partial charge on either side of this is 0, because we have a positive 2 charge in the center of the atom, and then we have a negative 1 charge on each. So half of the positive charge is divided among the 2 hemispheres of this atom, and therefore we have no net charge in any region of the atom. So right now, in this first example, we can say that this is uniformly, at least from our point of view, uniformly distributed or spread out, uniformly distributed electrons around the atom. Same thing here. This is just another way to uniformly distribute the electrons. The electrons are both roughly in the same place. If they're both in the center, that means they're kind of in the same area. So again, uniform. No net partial charges. Now, what happens if both electrons happen to end up on the same side or same hemisphere of the atom? Let's say the helium atom, remember, its electrons are free to move around however they want. We can't even predict it. Let's say both electrons end up on one side. What does that mean? That means this side of the atom, remember, atoms have a specific distance, and the definition of a dipole is just going to be charge, Q, charge Q times distance. That's what a dipole moment is. It's defined as the distance multiplied by the charge. Well, here we have all the negative charges on one side of the atom. Therefore, whatever positive charge is in the center of the atom is not being canceled out on the right side of the atom. So we have a partial positive on one side of the diameter of this helium atom, and we have a partial negative side on the other. We have ourselves a dipole, but this dipole didn't arise because of anything permanent. There is no permanency to this particular state of affairs. The electrons in the very next moment, the very next nanosecond, can rearrange themselves once again back to this or back to this sort of state or arrangement, or even arrange themselves back over here, allowing for maybe a lesser dipole, where maybe now instead of having negative two electrons on one side, maybe you have only one electron on this side and 0 electrons on this side. So instead of having a bigger dipole with 2 versus 0 electrons, maybe you have only 1 electron versus 0. So you have a lesser dipole, but you still have a dipole. Whereas over here, you have 0 dipole because there is no one side that has more electrons than the other. The point of all these pictures is to show that there arises the possibility, as long as electrons are free to move around, the possibility can arise that the electrons will be non-uniformly distributed, sort of crowding together in one part of the atom. And what goes for atoms also holds true for molecules, even more so because molecules tend to have more than one atom, multiple atoms. Therefore, they have more electrons to be non-uniformly distributed. The more electrons you have, the more likely it is that you're going to give rise to the London dispersion force and these temporary dipoles, because the more ways there are to rearrange or to have the electrons non-uniformly or unevenly spread out among the molecule. So molecules have an even greater tendency to have London dispersion forces. I'm using the atom as an example, a helium atom, because it's simple to view, it's simple to picture 2 electrons being unevenly spread out among the across the atom. But what holds true in these pictures for an individual atom will hold true even more so for a molecule. This is the basis of the London dispersion force, the temporary instantaneous dipole. And of course, if it's instantaneous, that means it arises quickly, but then quickly disappears because it can, whatever state or whatever cause those electrons to be in one place at a time isn't a permanent feature of the atom. Those electrons are buzzing around like bees. Yeah, two bees can be nearby at any given moment, but then they can quickly fly away. Also, electrons have electron-electron repulsion. So they're not going to get too close to each other too often. So this is a very weak force, and it only arises by chance. But among a population of quadrillions multiplied by even more quadrillions of atoms, of course, there are going to be plenty of atoms that have some kind of London dispersion force, some sort of temporary dipole. Moreover, those temporary dipoles are going to influence other atoms nearby that either collide with them in the gas state or happen to be with them and near them in the liquid state. They're going to influence each other through what's called an inductive effect. This is the induced dipole. Let's take a look at that idea. So dipoles are contagious. In other words, if one atom or molecule has a dipole, depending on the so-called polarizability of the atom or the molecule, it can influence its fellow atoms or fellow molecules to also gain a dipole, even if they didn't have one at first. That's because charges can be felt across space. Now, these are very short distances, meaning these atoms have to be very close to each other and for at least an appreciable amount of time. They should either be in the liquid or solid state, or they should be moving much more slowly in the gas state and just have enough time to influence one another. So if you look at this picture here, I'm using the same picture as before. I have a temporary dipole in this particular atom, meaning that its partial positive charge is emanating outward, and that partial positive charge is going to influence this atom, which doesn't even have a dipole at the moment. But what happens? Well, this atom feels the positive charge from that one, and the electrons, one or more of the electrons will respond to that positive charge, because remember, electrons are negatively charged, they are drawn toward positive charge. So as a result of that, these electrons may actually be attracted to the positive charge of the other atom's dipole, and those electrons will now have moved over to the left side of that atom. Now you have, where before you had only one atom with a dipole, you now have two atoms of the dipole. One dipole gives rise to another. This is induction, and this is the inductive effect. Inductive, meaning charge gives rise to charge to the extent that the other thing being influenced is polarizable, meaning it's able to be turned into a polar molecule or a polar atom. So helium number 1 induces, remember the word to induce something, to induce someone means to influence them or to make something happen. You can induce someone to do something you want them to do. You can induce labor, by the way. If a woman is pregnant, you can induce her labor by, beforehand, before her term is up, by giving her a cocktail of drugs to induce labor. Sometimes that's convenient for whatever reason. Anyway, so to induce is to make something happen through influence. So induce, inductive effect, depending on the polarizability of an atom or a molecule, you can induce one atom or molecule to take on a dipole where it didn't have one before. So a new dipole was created. New induced dipole. So one charge gives rise to another through the inductive effect. And this happens through bonds as well inside of molecules. So London dispersion force depends on electrons being unevenly distributed. With 2 electrons, there really aren't that many ways and the electrons can be distributed unevenly for one thing. And for another, there are only 1 or 2 electrons, so the force is kind of weak because remember, the dipole, the strength of the dipole, the magnitude of the dipole really depends on the strength or the magnitude of the opposite charges. With only 2 electrons and 2 protons, that's a pretty low level of charge. On the other hand, take something like, for example, xenon, where you have 54 electrons. Now, it's not very likely that all the electrons are going to be on one side of one hemisphere of the xenon atom at one time. So this is the left hemisphere, the right hemisphere. That's not likely to happen. Nevertheless, the more electrons you have, the greater the possible ways to rearrange the electrons, and that the greater possible ways the electrons will rearrange themselves in order to give rise to an unequal distribution. Remember, it only takes 1 or 2 electrons on one side of the atom to have that side of the atom more negative than the other side. So this side of the xenon atom will be, in this picture, is going to be very negative. And this side of the xenon atom will be very positive because a lot of the electrons have left. But remember, the fact that the electrons have left does not change the number of protons in the nucleus. It's sort of like uncovering that positive charge in the center. Now that the electrons aren't there to block that positive charge, the positive charge can emanate outward, influencing other atoms and other molecules around it. Because there's the loss of that blanket of electrons on that side of the atom has caused this to have an effect outside beyond the so-called borders of the xenon atom. And you can see the effect. You can see the effect that the number of electrons, which from now on, we're not going to count electrons. Instead, we're going to relate this to molar mass, molecular weight, or atomic weight. Atomic weight or molecular weight, either way, the London dispersion force is stronger in compounds and atoms that have higher atomic weights and molecular weights or molar masses. And you can see the effect. Helium is the lightest knowable gas. It has only a 4 gram per mole atomic weight, and its boiling point is just a few Kelvin degrees or Kelvin units above absolute zero. But when you get to neon, with its 20 gram per mole atomic weight, you can see that the boiling point has jumped. Now, why am I using boiling point? Boiling point is a sort of indirect measure of the strength of the intermolecular forces. All else being equal, the stronger the intermolecular forces, the more the atoms and molecules stick to each other. Intermolecular forces, remember, are forces of attraction between two different atoms or two different molecules. I mean, when I say two different, I mean two atoms or two molecules, whether they're the same element or the same molecule or not, they are two different instances of that molecule. So the stronger the intermolecular forces, the more they stick together, the harder it is to boil them. So as strength of intermolecular force increases, the boiling point also increases, or in other words, the temperature you need to reach in order to separate those atoms and molecules from one another goes up. In other words, it becomes harder to boil. A high boiling point indicates difficulty or having to put extra energy into separating two atoms or two molecules from each other in the liquid state. So as we keep going down, you notice all of these noble gases get heavier. Their atomic weights are going up, and their boiling points are also getting higher. These two things move together. The boiling point and the atomic mass of noble gases, and of course, and the molecular weight of most molecules are directly correlated. They are directly proportional. That's because the more electrons you have, the greater the molecular weight you have, because probably you have a bigger atom. That's the reason. It's not the electrons themselves. How do I put this? It's not the weight of the atom itself. It's the fact that you are using atomic weight as a proxy, as a substitute for counting electrons. And we're using boiling point as a gauge of how strong the intermolecular forces are. So you can see the clear trend here, going from 4 Kelvin, just 4 units above absolute zero, all the way to 167 Kelvin. Or, well, I'm not going to try, I think it's negative 106 degrees Celsius. Still 106 degrees below zero, below freezing. So 167 kelvins. Remember, these are kelvins we're looking at here, not Celsius, kelvins. Helium does not boil at 4 degrees Celsius. It boils at super freezing temperatures. All atoms and molecules have the London dispersion force, all of them. It's not just atoms, it's not just nonpolar molecules. All molecules, whether they're polar or not, have the London dispersion force. It's only a question of whether it's the major kind of intermolecular force of attraction. In nonpolar molecules, London dispersion force is the only kind of intermolecular force of attraction. But in polar molecules, those with permanent dipoles and hydrogen bonding and electrostatics and all those other things, the London dispersion force is present, but it doesn't really matter because it is overwhelmed by the stronger types of intermolecular forces of attraction. Permanent dipoles, gram for gram, or molecular weight, gram per mole, molar mass unit per molar mass unit, are much stronger. So boiling point, melting point, vapor pressure, all else being equal, density are all related to the strength of intermolecular forces within atoms and molecules. All these physical properties depend on the intermolecular forces of attraction, boiling point, melting point, etc. That's why we tend to focus on boiling point as a measure of the strength of intermolecular force. We could use melting point if we were talking about solids. We could use vapor pressure if that were just a little bit easier to imagine. You know what vapor pressure is, but it's the tendency of a gas to volatilize, to enter its gas phase from the liquid phase. Okay, London dispersion force as a function of molecular weight. So you just saw that as you increase atomic weight, the London dispersion force gets stronger, and you can see the result of that in the higher boiling point. Well, as I said, the same thing holds true for whole molecules, not just for individual atoms. Nonpolar molecules with a relatively high molecular weight will experience stronger London dispersion forces because, again, you have more electrons. A big atomic weight indicates a big atom. You know, when I say big, I mean like carbon, nitrogen, as opposed to hydrogen or helium. Bigger atom, which of course will have multiple layers of orbitals, which will have multiple electrons. And the more electrons you have, the greater the London dispersion force. Although London forces are weak compared to the dipoles, to permanent dipoles, and especially the hydrogen bonding type of dipole, with enough atoms or molar mass, the strength of London forces can match that of a permanent dipole and even exceed a permanent dipole's intermolecular force. There are, of course, non-polar molecular compounds that have higher melting points and higher boiling points than polar compounds. They're generally composed of a lot more atoms, though. A quick and simple way to compare the strengths of intermolecular forces between molecules is, of course, to compare their melting and or boiling points. So let's take a look here. We have water. Water has only 3 atoms in it. 3 measly atoms. It has only an 18 gram per mole molar mass. 18 grams is nothing. That's a very small molecule. And yet water has one of the highest boiling points. It's 100 degrees Celsius to boil water. 100 degrees Celsius is extremely high for a tiny molecule like that, I mean. Okay, so let's compare water to some different hydrocarbons. Now recall, and this is something you need to remember. Recall that hydrocarbons are non-polar. The simplest hydrocarbons are non-polar and they have the formula CXHY, meaning they are only composed of carbons and hydrogens. They are non-polar. You must commit this fact to memory. It's going to come up over and over again. Okay, so let's compare water. Let's first compare water, which has 18 grams per mole molar mass, to its closest hydrocarbon analog. Well, not analog, but its closest weight class. In its weight class, you have the 16 gram per mole methane. Methane, of course, as you know, is the simplest hydrocarbon, CH4. So methane has a molar mass of 16, comparable to the 18 grams per mole for water. Do they have similar boiling points? No. Methane boils at negative 162 versus the 100 degrees Celsius for water. There's a 262 degrees Celsius difference between water's boiling point and methane. Methane boils at temperatures that the Earth has not even experienced. It's so cold. There are methane lakes and rivers and oceans on other planets that get a lot colder than Earth. But here on Earth, you'll almost never see methane as a liquid unless you pressurize it or supercool it. That's a measure of the relative weakness of methane's intermolecular forces. Why is that? Because methane is a non-polar molecule. And as a non-polar molecule with a relatively low molecular weight, it has only the very weak London dispersion forces. Now, London dispersion forces can be strong if you've got a significant molar mass, but 16 grams is not really all that significant. Okay, so methane is clearly methane molecules are very, very weakly attracted to each other. They barely touch at all. In other words, to liquefy methane, you have to lower the temperature to 162 below zero, below the freezing point of water. How about butane? Butane is lighter fluid. It has a molar mass of 58 grams per mole, significantly higher than water. In fact, it's about triple that of water. But again, it's a simple hydrocarbon, so it's non-polar. Its boiling point is 0. Now again, compare that to water versus 0 degrees to freeze water. Water is freezing when butane is boiling. Water is freezing when butane is boiling. Butane's intermolecular forces are so weak that at the temperature that would freeze water into a solid, butane molecules have enough energy to blast apart from one another and go hurtling through space at hundreds of meters per second, flying away from each other. They have overcome their intermolecular forces of attraction so thoroughly that it's become a gas. So butane clearly is no match as far as strength of intermolecular force of attraction, is clearly no match for water, despite the fact that butane has triple the molar mass. So all that London dispersion force just doesn't hold up to the hydrogen bonding available in water. Hydrogen bonding, gram for gram, is a lot stronger than London dispersion force. You can see the relative strengths and the relative effects on boiling point. Okay, finally, let's get to heptane. Heptane has a molar mass of 100 grams per mole. 100 grams, that's more than 5 times the molar mass of water. And finally, at 23 atoms and 5 times the molar mass, you finally find a hydrocarbon that has a comparable boiling point to water, meaning you can say that its strength of intermolecular force, the London dispersion force, is finally on par or comparable to the strength of a hydrogen bonding molecule like water. But it took 5 times the molar mass and 23, so 7 times the number of atoms to get there. So the London dispersion force can equal the hydrogen bonding or a dipole-dipole force, but you need a lot of atoms with their electrons being unevenly distributed in order to get there. So finally, you have heptane, which is comparable to water, but it's a much bigger molecule, both in terms of weight and in terms of number of atoms compared to water. Other nonpolar molecules, other than the hydrocarbons, I don't want you to think hydrocarbons are the only nonpolar molecules. We have sulfur trioxide. This is also a nonpolar molecule. And if you don't know that, make sure you're able to draw a Lewis structure, predict the molecular geometry from that Lewis structure, and then work out the dipoles and see that all those sulfur-oxygen dipoles cancel each other because this is trigonal planar, not trigonal pyramidal. There are only 2 possibilities, right? So sulfur trioxide is a nonpolar molecule, despite the fact that all of its bonds are polar. It has an 80 gram per mole molecular weight, and it boils at 45 Celsius. I mean, it's not too bad. At least it boils above room temperature. Hexane has a comparable molar mass of 86. Now, if it's within a few molar mass units, it's okay. So 86 versus 80, close enough for our comparison purposes, right? 86 versus 80 grams per mole. Hexane, on the other hand, has a boiling point of about 70 degrees. Well, okay, 70 is a little bit higher than 45. Nevertheless, they are at least in the same ballpark. If you compare 160 versus 100, those are 260 degrees apart. Here, at least, these are kind of comparable. They're both hot, but still within shooting distance of room temperature, which is 25 Celsius. 45 degrees is a pretty hot day in the desert. 70 degrees is, well, more than any temperature I ever want to see boiling either for water. So they're within spitting distance of each other. Let's put it that way. And their molar masses are comparable. They're both nonpolar molecules. The structures are different, and that probably accounts for why their boiling points aren't totally in sync with each other, but they are comparable at least. They're both nonpolar molecules that rely on the London dispersion force to attract their fellow molecules. So sulfur trioxide molecules coagulate, or coalesce, or liquefy based on London dispersion forces, just like hexane molecules do. But if you add enough heat and raise the temperature to 45 degrees Celsius for sulfur trioxide or 70 degrees Celsius for hexane, that's enough energy that you're supplying to blast these liquids apart into gases. Another one, dimethyl sulfoxide, down here below, has this formula right here. Again, comparable molar mass, but the big difference is, look at the boiling point here. Dimethyl sulfoxide, instead of being around 45 or 70, has a boiling point even above that of water, 189 degrees. That's almost triple the benzene, and about 4 times, actually more than 4 times that for sulfur trioxide. So it's a much higher boiling liquid. Why is that? Dimethyl sulfoxide, unlike sulfur trioxide and hexane, even though it has a comparable molar mass of 78 versus 80 versus 86, it has a dipole. It has a net dipole between the sulfur and the oxygen. And I'll draw the little structure for you here. I kind of gave a hint of the structure over here by having the methyl, the CH3 groups attached to the sulfur, and the sulfur is double bonded to the oxygen. There is a net dipole here, and that is what gives this the high boiling point. We have the net positive on the sulfur. because you have a net dipole, there's going to be a lot more stickiness between the DMSO, the dimethyl sulfoxide molecules. They're going to, one dipole, remember, attracts another, and they stick together like Velcro. It's like having a piece of Velcro on your molecule. When they hit each other, they could hit each other with enough force to bounce off, but if they hit each other the right way, and if they slow down a little bit, those little patches of Velcro known as the dipoles are going to stick, and then the molecules are going to stick. And then if enough of them stick together, you have a liquid rather than a gas. So let's just do a little London dispersion concept check. Which of the following is likely to have the lowest boiling point? Another way that I could have asked this more directly would be, the question could be asked this way. In other words, lowest, which has the weakest intermolecular force of attraction. And then if we decide that all of them, if all of them have the same force, they don't, but if all of them have the same force, which has the lowest molar mass or molecular weight. Okay, so let's take a look at these. Let's look at our options. We have, okay, the first two are pure hydrocarbons. So automatically you should be focused on those. In fact, at this point, you are pretty safe in eliminating just about every other option here. The silicon might actually be another possibility, but chances are that's not it because it looks like it has way too many atoms compared to these. So we have propane and we have pentane. They're both hydrocarbons, simple hydrocarbons. Propane has a, has a molar mass of 44 grams per mole. And pentane has 72 grams per mole. Okay. Pentane has 17 atoms, propane has 11 atoms. Sorry about that. How about this one? This is not, what is this? This was supposed to be octane. This was supposed to be a hydrocarbon. I'm sorry, this, C8F16. Tell you what, let's use that. Let's use that. This is not octane. Let's get rid of that. C8F16. How about this one? Well, this is carbon with a bunch of fluorines. However, I'll let you in on a little secret. This is a nonpolar molecule. Nevertheless, you've got 16 fluorines. That's 8 times 12 plus 16 times 19. Huge molecular weight or molar mass. Just enormous compared to the other ones, right? This is going to be probably over 300 grams per mole or more. I'm not going to calculate it right now, but it looks like a lot, right? You've got 320 plus, actually you may even have over 400 grams per mole. So this is a very large molecule. Chances are it's not going to have a very low boiling point. How about PCl3? Well, that's only 4 atoms, right? 4 atoms, but what type of, so far, all the ones we've looked at have been London dispersion force. A through C are London forces. How about PCl3? It's got only 4 atoms, but PCl3 is a trigonal pyramidal structure, which makes this polar. It's a polar molecule, and therefore it has the dipole-dipole force. Dipole-dipole force is always going to be stronger than any kind of comparable London dispersion force, gram for gram. And PCl3 definitely has a higher molar mass. Chlorine all by itself has a 35 gram per mole mass. So this is going to be well over 150 grams per mole. So because of that, we know that it's still looking like one of the first two. Silicon, this is called tetramethylsilane. Now this one is also nonpolar. So because this is nonpolar, it's also got London forces. In fact, I'll draw it for you. I can represent the carbon with the 3 hydrogens, the so-called methyl groups, like this. Each one of them is equal in terms of electronegativity. In other words, basically, these are all nonpolar bonds, and this is a tetrahedral shape. If you have the same groups of atoms around a tetrahedral shape, you've got a nonpolar molecule. So this is London. But 1, 2, 3, 4, we've got 4 times 12 for each carbon, plus we've got the silicon. We've got about 80 to 90 grams per mole. We've got about 90 grams per mole here. This is a possibility, actually. Let's see. It's in the running. It's got London dispersion force. So we've got A is London, B is London, C is London, D is dipole-dipole, and then E is London again. So we can already eliminate the dipole-dipole. And so how do we sort the rest of these? Well, we know that the higher the molecular weight or the molar mass, the stronger the intermolecular forces. But we're looking for not the strongest, but the weakest. We're looking for the lowest boiling point. So step 1, eliminate dipole-dipole as an option. The dipole-dipole force, the polar molecule, i.e. the polar molecule, as an option. So now we're down to simply A, B, C, or E. Step 2, compare molar masses, which we kind of already did. Step 3, because we're looking for the lowest boiling point, not the highest, step 3, pick the lowest molar mass. So in this case, that's going to be the propane. Propane has about a 44 gram per mole molar mass. So propane is it. The others all have higher, 72. This one is going to be some massive amount, greater than 400 grams per mole for option C. E has a greater than 90 gram per mole. All of them are too high, or excuse me, all of them are higher than propane. It's all relative. I don't know what the boiling point is off the top of my head. I know it's below 0 for propane. I'm not sure exactly what it is, but I do know that in this group, propane has the lowest molar mass, and it is a London dispersion force nonpolar molecule. So because it has the lowest mass, it must also have the lowest boiling point. Remember, when you're looking for the lower boiling point, you're looking for weak intermolecular forces. Easy to boil. Lowest boiling point means easiest to separate the molecules or the particles. So keep that in mind. If we're looking for the highest boiling point, we'd probably have a toss-up between, we'd probably pick option C because of its massive London dispersion force, even more so than PCl3 with its dipole-dipole, only because 24 heavy atoms is quite a lot. 400 grams per mole is not at all a fair comparison. When you compare molecules, generally speaking, they should be, the way to really make them comparable and to see if which one has the stronger intermolecular force is usually to compare molecules of similar molar mass. Like I did in the previous example here, sulfur trioxide, hexane, and DMSO, dimethyl sulfoxide, all had similar molar masses, so they were comparable. It wouldn't really be fair, and it wouldn't really be predictable to take a massive nonpolar molecule and compare it to a tiny polar molecule, which was what I did with heptane and water. But of course, I didn't ask you that question. I presented the information to you as an example of the effects, but I would not ask you, well, now that you know, maybe I would, but I wouldn't give you two molecules you've never seen before of very different molar masses and then say, well, pick which one has the stronger intermolecular force or higher boiling point. One's polar, one's not, and you don't have any which way of knowing because the one with London dispersion force has a much higher molar mass. Molar mass can turn a weak London dispersion force into a very significantly strong intermolecular force. So you have to compare molecules of similar molar mass. On the other hand, if you have a very lightweight nonpolar molecule, then it's clearly always going to be the lowest boiling point, the weakest intermolecular force. And if you have a very high molecular weight, polar or hydrogen bonding molecule, then yes, of course it's going to have the highest boiling point and it's going to have strong intermolecular forces. And if you put an ionic compound in the mix, the ionic compound is always going to have the strongest intermolecular force because electrostatic beats all. And it's going to have the highest boiling point because ionic compounds have super high melting and boiling points because of their strong electrostatic force. Electrostatic forces, interactions beat any kind of intermolecular force. Electrostatics, remember, molecular compounds are brought together by partial charges. Ionic compounds are brought together by full charges. It's the same charge, only now you've got the complete version of it. It's a difference between a lawnmower engine and a Ferrari engine. They're both engines, but there's a big difference between them. Okay, let's continue on. Hydrogen bonding. Let's talk about hydrogen bonding more specifically. So water is the most polar molecule probably ever because all water is hydrogen bonding. Water is pure hydrogen bonding. Look at the structure of water, HOH. A hydrogen bond is defined as a bond between a hydrogen and either oxygen or a fluorine or a nitrogen. Water is two hydrogen bonds together in one molecule. It's all hydrogen bonding. So water is the preeminent example of hydrogen bonding, but it's not at all the only example. There are billions of compounds that have hydrogens bonded to oxygens, and there are billions of compounds that have nitrogens bonded to hydrogens. There's only one compound that has a hydrogen bonded directly to a fluorine, and that's hydrogen fluoride. That's it. Remember, fluorine can only have one bond and hydrogen can have only one bond. So there really is no other way to make a hydrogen bond between hydrogen and fluorine because once you connect them, they are done. Fluorine cannot bond to anything else. Any other bond is disallowed because fluorine can only create one bond other than a superacid, which we're not going to worry too much about in this class. Other than one particular superacid. It's a superacid because fluorine hates bonding to more than one thing. Okay, so hydrogen bonds are especially polar due to the fact that hydrogen has an electronegativity on the Lewis scale of about 2.1, and fluorine, oxygen, and nitrogen are the three most electronegative elements, 4.0 for fluorine, 3.5 for oxygen, and chlorine is a 3.0. So these are the most electronegative elements. So it's the greatest imbalance in electronegativity of most of bonds, at least as far as the most common types of bonds. Yes, there's phosphorus and there's some semi-metals out there, but those are not nearly as common as having hydrogen bonded to oxygen or nitrogen. So common that is that it's actually a major part of what builds our bodies. We are made of hydrogen bonds between hydrogen and oxygen and hydrogen and nitrogen. We are literally built from that. And I'll show you what I mean by that in a few slides. So because of this, it's an especially strong type of dipole. It is simply a dipole. It just happens to be a strong one. It differs in magnitude, but not in kind. It's not a fundamentally different type of force. But remember, even a partial charge is nothing compared to an integer, a whole number charge. The attraction between +1 and -1 is far greater than the attraction between even the strongest partial, plus 0.02 versus fluoride minus 0.02. -1 beats -0.02, +1 beats plus 0.02. And these are the actual kinds of numbers I'm talking about, fractions of charges. So remember that ionic compounds are always have a greater interparticle attraction than any molecule, than any atoms, and any dipole will attract another dipole. I'm not talking about covalent bonds. I'm talking about the bonds that form between two covalent bonds. The bond between bonds. Okay, let's look at some hydrogen bonding example. Actually, this is not just hydrogen bonding. We'll go through this as a hydrogen bonding example, but let's name all the kinds of bonds, intermolecular forces that actually exist in each one of these molecules. And they're all molecules. I didn't put any ionic compounds here. So let's take a look. Okay, so which ones exhibit hydrogen bonding? The first option is ammonia. I didn't draw it because I know you know the molecular geometry and the structure of ammonia. Nevertheless, I'll draw it now. But on your own, I want you to be able to draw this yourself quickly and easily. That's why I didn't draw it here for you. So we have ammonia. I'm not going to bother with the lone pairs. It's just going to clutter up an image that we don't really need cluttered. Notice I didn't put lone pairs on anything, though a lot of these atoms should have them. There's just no need right now. We know, as long as we know what the shapes are, we don't have to worry about the lone pairs at this point. We just want to see the shapes so that we can figure out whether the dipoles cancel or not. And of course, we're looking for hydrogen bonding. So for this first example, do we have hydrogen bonding? You can pause the video here and try to answer this for yourself. 3, 2, 1. Okay, and you're back. So what's hydrogen bonding? Remember, hydrogen bonding is a bond has a bond directly between hydrogen and nitrogen. So ammonia is nothing but hydrogen bonding, just like water, it's all hydrogen bonding. So we have an H bonded to N. So yes, indeed, hydrogen bonding it is. This is a hydrogen bonder. How about methane? Well, we've got a bunch of hydrogens. Does that say much? Let's see. Let's draw it. We have hydrogen. So we have our tetrahedral shape. So this is nonpolar automatically. Just knowing it's nonpolar, you should eliminate any kind of any version of dipole-dipole force. But putting that aside, do any of these bonds represent a hydrogen bonding bond? No. Hydrogen can't just be connected to any old atom. It has to be phone. Remember your cell phone, phone? Well, phone, F-O-N. Spell phone funny and you get the atoms that are associated with hydrogen bonding, fluorine, oxygen, and nitrogen. So hydrogen is not combined with directly attached to anything, fluorine, oxygen, or nitrogen. This is not a hydrogen bonder. In fact, what kind of intermolecular force do we have here? It's a nonpolar molecule. It's a hydrocarbon. This is London dispersion. Any nonpolar molecule has London dispersion forces as the only type of intermolecular force. Next one, we have ethanol. Here's the structure for ethanol. So then the question becomes, is this a hydrogen bonder or not? Well, what types of forces do we have? Do we have hydrogen bonded directly to fluorine or oxygen or nitrogen? Yes, indeed we do. We have it right here. This is hydrogen bonding, so H bond. What other kinds of intermolecular forces do we have? Just because we identified one doesn't mean there aren't other types of intermolecular forces that are available. We do have other forces. For example, we have this bond here, carbon-oxygen. This is a simple this is a regular run-of-the-mill dipole-dipole force. And then, of course, all molecules, regardless of size or anything else, the rest of the molecule, of course, would have London dispersion. But this part especially, this very non-polar region here, would be mainly London dispersion. There are no positive or negative charges in this molecule, so there's no electrostatics, and it's not dissolving anything. It's not like it's taking an ionic compound and dissolving it, so there's no ion dipole force here. But you do have the other three. You have all three of the molecular forces represented. You have dipole-dipole, you have London dispersion, and you have hydrogen bonding. And that's often going to be the case. Just having one intermolecular force doesn't preclude others from being part of the atom. or the molecule. Atoms, by the way, can only have one type of intermolecular force, London dispersion. Since there is no bonding, there is no dipole across a bond. So London dispersion is it. Okay, how about this one? Acetic acid. I'm going to let you in on a little secret. All carboxylic acids, all the organic acids, the carbon-containing acids, have hydrogen bonding and dipole-dipole, and a lot of them even have a significant portion of London dispersion. So, but let's first identify the hydrogen bonding portion of this. Here we are. Here's the hydrogen bonding, H bonding. But we also have this part here. This is dipole-dipole. Remember, carbon bonded to oxygen is a dipole. Now you might say, well, wait a minute, in carbon dioxide, you've got two oxygens and they cancel. Yeah, but look at the shape. This is trigonal planar. These are 120 degrees. There is a net dipole that points right in between these two oxygens. So there is a net dipole. That's why this is dipole-dipole. The net dipole points outward from the carbon in between the two oxygens, the net dipole. And of course, there is a significant portion here of carbon to hydrogens. There is some what's called aliphatic portion of this, a hydrocarbon portion of this. We have this part right here. In fact, this molecule looks a lot like the other one, except the other one, the ethanol, didn't have the double bond to the carbon. So this is London. This portion of the molecule is London. It's the part that doesn't matter that much. Whenever you're looking for intermolecular forces, you always look for the one major type of intermolecular force, the one that's going to define the reactivity and the physical properties of the molecule. And that's always going to be the strongest intermolecular force you can find. So even though these both ethanol and acetic acid have three different kinds of intermolecular force, it's their hydrogen bonding that is going to be the most important thing to us, because that's really what's going to be the defining factor of their physical properties. It's going to be the thing that dictates the relative boiling points, melting points, vapor pressure, density, and miscibility, meaning how well it mixes with other liquids, etc. It's the hydrogen bonding that's going to matter the most. So always look for the biggest or the most important or the most major, strongest type of intermolecular force. And generally, when I ask a question, I always ask that way. What's the major type of intermolecular force? I don't mean identify every single intermolecular force. I'm doing that here because we're practicing. But generally speaking, you really only care about one force, and that's the strongest force that you can identify. Okay, how about the next one? Difluoromethane. We've got what looks like methane, but we've replaced two of the hydrogens with fluorine. So we've got hydrogen and fluorine in the same molecule. Does that mean anything to us as far as hydrogen bonding goes? Well, the question is, are these hydrogens directly connected to the fluorines? No, they're not. There's absolutely zero hydrogen bonding in this molecule. No hydrogen bonding whatsoever. No H bonding. No H bonding because it's not enough to have hydrogen and fluorine in the same molecule. They must be bonded to each other. There must be a dipole difference, a dipole arising from the strong difference, the big difference between fluorine and hydrogen. Hydrogen's connected to carbon. Their electronegativities are so similar, we don't even consider this bond polar. For all intents and purposes, the bottom half of this molecule is non-polar. So there's no hydrogen bonding here. However, that doesn't mean there's no dipole. There is a dipole. We have a dipole, a net dipole pointing straight up in between the two fluorines. There's a net dipole pointing straight up from the carbon toward the middle of the two fluorines because we have two dipoles. Carbon-fluorine is a polar bond. So there is a net dipole, and anytime there's a net dipole and it's not hydrogen bonding, it's the dipole-dipole type of force. This is a polar covalent molecule. Therefore, it has the dipole-dipole intermolecular force of attraction. Just look at it this way. We are now putting a name on what we used to just call the polar molecule. Now we're naming the force in that polar molecule. I'm going to say that again. We are naming the force in that polar covalent molecule. Before, we were just naming the molecules as either polar covalent or non-polar covalent, polar molecule or non-polar molecule. Now we're actually giving a name to the specific force within that molecule that makes it polar or non-polar. Okay, so dipole-dipole. Just having two hydrogens isn't enough to call this London dispersion force. For the most part, the London dispersion force is absent from this because there isn't another carbon that's free of any kind of halogen. If there were another carbon bonded nothing but hydrogens, I would say that maybe there's a London dispersion portion to this, but there isn't. So there's no London there either. The hydrogens don't count. You need like at least one carbon with nothing but hydrogens attached to it. Okay, the next one, hydrocyanic acid. Again, I didn't bother drawing this because I know you know how to draw this. So make sure you know how to draw this, hydrocyanic acid. Make sure you recognize acid names. Hydrocyanic acid is simply hydrogen cyanide. Cyanide is CN, so let's draw this. So hydro, single bond between hydrogen and the carbon is triple bonded to a nitrogen. Again, I'm not going to bother with the lone pairs here because that's just going to clutter up our beautiful drawings. Okay, maybe not that beautiful. This is a linear molecule. We already know this is polar, don't we? It's a linear molecule, yeah, but even though there are no lone pairs on the central carbon atom, we do have dissimilar elements on the outside. So nitrogen and hydrogen, massive imbalance in terms of electronegativity. So we know this is a polar molecule. We know the nitrogen is partially negative. We know the hydrogen is going to be partially positive. In fact, we even know that the carbon is going to be partially positive. So there is a net dipole pointing toward the nitrogen. So this is definitely dipole-dipole. Now, for anyone wondering why this isn't hydrogen bonding, no hydrogen bonding, just because we have hydrogen and nitrogen across from each other does not make this a hydrogen bond. Remember, this bond is between hydrogen and carbon. And there's only a tiny, tiny dipole between hydrogen and carbon. They're, in fact, so small that we consider this nonpolar. In other words, no HN bond. There is no direct hydrogen to nitrogen bond. Just because they're in the same molecule, just because you see them in the same formula, does not mean that they are bonded together. They must be connected. Okay. Next molecule is acetone, a very common lab reagent, actually a very common lab cleaning solvent. That's actually the biggest use of acetone, more of as a cleaning solvent than anything else. Okay, let's take a look. So we have a bunch of hydrogens and we do have oxygen. Does this make a hydrogen bond? Absolutely not. In order for this to be a hydrogen bond, one of these hydrogens would have to be directly connected to oxygen, which it is not. Therefore, there is no fluorine or nitrogen. So this is definitely not a hydrogen bond. No hydrogen bonding. This is not it. But let's see what it does have. It does have a dipole-dipole though. So because it's a because it's a polar molecule, it does have dipole intermolecular force. So it has that. It's got that going for it. It's got a net dipole there. Also, because it's got a significant number of carbons with nothing but hydrogen around them, both here and here, I'm going to call this part the London part of it, the London dispersion part. So these carbons, this chain of carbons here, kind of makes up a sort of, small region of London dispersion force. Now, again, all atoms and molecules have the London dispersion force, including the one I said, including difluoromethane, where I said it didn't have any significant London dispersion. That doesn't mean it doesn't have any. Remember, London dispersion force exists in all atoms, individually and as molecules. I'm just labeling these according to the significant portion of the molecule that is not anything else. That's all I'm labeling here. So for example, in this previous example of hydrocyanic acid, there really is there's no appreciable amount of London force either because everything's involved in a dipole somehow. But these carbons over here in this molecule in acetone, they really aren't involved in any kind of dipole interaction. That's why I labeled them as London dispersion. Here, these hydrogens are really part of the carbon, which is part of a dipole. So I don't really bother labeling that London dispersion. There's no extended region of nonpolarity, not enough to really consider. Two atoms don't make a London dispersion portion or moiety on a molecule. Yeah, I used the word moiety. Moiety just means a significant part of a molecule. Don't worry if you don't know that word. I'm not going to expect it, and I don't like using it very much. Okay, how about the next one? We have trimethylamine. Again, because I don't expect you to know the formula for something called trimethylamine, I drew it in for you. If I give you stuff like this, I will give you the structure. I don't expect you to know what trimethylamine is. We didn't learn organic compound naming. Okay, so again, we have a bunch of hydrogens and we have a nitrogen. In fact, this is very much an ammonia analog. This is an ammonia derivative. Actually, this goes one way. It's an ammonia derivative this way. All we did was we took the hydrogens and we put methyl groups. A methyl group is a group of CH3, methyl. Methyl group, wow, it's only one L. CH3, a carbon with 3 hydrogens bonded to something else. So these are called methyl groups. I'm only saying that just because, just so you know what I'm talking about here, that's all. It's not something, that's a little bit, again, that's organic naming. It's a little bit beyond the scope of this, it's beyond the scope of this class. But sometimes I have to communicate with you and I don't want to just spend 100 words to say something that one phrase will tell you what I mean. So 3 methyl groups, note that they are all the same, but regardless, this nitrogen does have a lone pair on the center, so that makes this trigonal pyramidal. But the question is, do we have hydrogen bonding? Well, the hydrogens are bonded to carbon, not to nitrogen. Not one of these hydrogens is bonded to the nitrogen, therefore, no hydrogen bonding. Unlike the ammonia that this is derived from, there is no hydrogen bonding in this molecule. Nevertheless, there is a significant amount of dipole-dipole. This is a trigonal pyramidal molecule. Had I drawn this correctly, here, let me just quickly draw it for you, then I'm going to erase it to make room. Had I drawn this correctly, it would have looked like this. When I say correctly, I mean, had I drawn it with its correct molecular geometry being obvious, I would have drawn it like this, as a trigonal pyramidal molecule. And so there would be a net dipole pointing upward, up and through the middle. The carbons would be donating electrons to the nitrogen, and so you'd have a net dipole. Net dipole means you have a polar molecule, and therefore it's the dipole-dipole force. Since there's no hydrogen bonding, the only other option for a polar molecule is dipole-dipole. There is a significant amount of London dispersion force. I'm just not going to bother writing it in, getting crowded and messy already, but there is some London dispersion force with each one of these carbons. It's actually kind of significant. Here, I can write it here, London. The methyl groups together make up a sort of London region of the molecule. But it does have a net dipole, so it's one of those molecules that are sort of, they're polar, but they're very sort of lightly polar. They can kind of get along with both polar and non-polar molecules. In fact, the more carbons you have added to a molecule like this, to a molecule that has a dipole, the less polar it becomes. Eventually, you can get to the point where you have so much London part to the molecule that it overwhelms whatever dipole there is, and the other molecules don't even see the dipole anymore. And the result is that the molecule that has a dipole, and that dipole, it's so overwhelmed by the nonpolar part of the molecule that it effectively becomes a nonpolar molecule. Okay, so let's get rid of this now. You have the picture on the video now. You can always rewind. Okay, the last one is the simplest of all. 2 atoms, right? 2 atoms, hydrofluoric acid. Remember, hydro implies this is a binary acid, so hydrofluoric, no oxygen, just HF. This is the only example of hydrogen bonding that involves fluorine, other than the superacid, which we're not going to talk about. Not really relevant to us. Hydrogen bonding for sure. Hydrogen bonding. Of course, this is a dipole-dipole, but it doesn't matter anymore because this is hydrogen bonding. And the only bond is hydrogen bonding. So that's it. It is a hydrogen. This is a hydrogen bond. This is it. HF is a hydrogen bond, and it is a hydrogen bonding molecule. The entire molecule consists of 1 hydrogen bond. Okay, so that's how you go through that. That's how you look at the forces. That's how you determine whether something's hydrogen bonding. And to tell you the truth, that's how you decide whether something's dipole-dipole or London dispersion or not. If it has, it's a sort of hierarchy. If it has anything other than London dispersion force, then it's really not about the London dispersion force. Dipole-dipole beats London. Hydrogen bonding beats dipole-dipole. It's sort of like a game of cards. And hydrogen bonding is a royal flush. And London is a pair of 5s. So, you know, it's a losing hand. So it's going to be at the bottom of the barrel. And electrostatic actually is the winning hand of all. I guess in this analogy, electrostatic would be the highest hand or the best hand, which would be to choose not to gamble at all. All right. Just taking a closer look at hydrogen bonding, I have here an example of methanol. Methanol is the liquid form of methane. Oftentimes it's transported as methanol, which is the alcohol form of methane. Methane is CH4. Methanol simply puts an oxygen in between one of the hydrogens and the carbon. So it sticks an oxygen in between and it becomes methanol. So that liquefies. The reason that liquefies is because it's heavier and because hydrogen bonding raises the boiling point of methane to methanol's boiling point, which is a little bit high, which is actually considerably higher. You can liquefy. Because of the hydrogen bonding, the molecules stick together. So we have the hydrogen bonding portion here and a hydrogen bonding portion here. The opposite partial charges are very much attracted to each other. Again, they are attracted to each other. The hydrogen is going to be attracted to the oxygen of another molecule, and likewise, the hydrogen is going to be attracted to the other oxygen of the other molecule. It's like Velcro. They stick together. As soon as they come into contact, they come together and it's hard to tear them apart. You can add enough heat and that will tear them apart, but it's got to be a higher amount than methane. Methane has almost no Velcro. So you've got the relation there, hydrogens and oxygens, opposite partial charges attracting one another. So 2 methanol molecules are going to stick to each other like the ends, like these tail ends here contain Velcro that they can overlap with each other. Here we have methanol and water. There's no rule that says a hydrogen bond can only occur between 2 of the same molecule. No, not at all. Any 2 hydrogen bonding molecules will be attracted to each other. In fact, any 2 molecules with similar types of intermolecular forces will be attracted to each other. They don't discriminate. So the oxygen the oxygen on this methanol molecule will be very interested in the hydrogen from the water and vice versa. Likewise, the oxygen on water is going to be very interested in the hydrogen on methanol. In fact, something occurs in chemistry, and this occurs 1,000,000 times a second. When you mix hydrogen bonding molecules together in a solution, in a liquid-liquid solution, what's called proton exchange occurs. This is such a well-known phenomenon that it actually affects the measurements of when you're analyzing molecules through something called nuclear magnetic resonance, which is, it's sort of like an MRI, but for molecules rather than for people. Anyway, this is such a well-known phenomenon that it actually affects molecules when you're trying to analyze them through a molecular kind of MRI, NMR. You can actually see that the hydrogens don't stick with the original molecules, but they get exchanged with one another. In other words, if I were to isotopically label, God, I think I'm getting a little bit overboard. Okay, this is definitely beyond, you can skip the next 2 minutes. This is a little bit beyond our course, but if you're interested, if you were to isotopically label the hydrogen here, in other words, if you were to use deuterium, the heavier type of hydrogen, the one with 1 neutron instead of 0 neutrons, and you were to put this methanol into a mixture with water, what you would soon find out is your water, a lot of your water molecules would end up getting the deuterated or the deuterium hydrogen instead of having plain old hydrogen. Even if you started off with plain old hydrogen in your water, eventually you'd notice that you have heavy water. You'd have water with deuterium hydrogens with hydrogen isotopes that are heavier. Why? Because of proton exchange. These hydrogens are so freely attracted to the different oxygens that they will actually leave and will exchange with one another, so that this will become, whoops, let me clear this up a little, so that by the time these two molecules are finished interacting with each other, what you'll end up with is actually this as your methanol and this as your water, not linear water. Please understand, it'll be bent. But this will be your new molecule, and this will be your new methanol molecule. The same thing can happen interatomically or even intermolecularly or intramolecularly as well. In other words, one methanol molecule can exchange its hydrogen with another one. So proton exchange is a real thing. That's how loosely hydrogens are held. And this, by the way, is why acids are such a common class of molecules, because hydrogens are easy to let go of in water. Because water is the ultimate hydrogen bonder, it is also the ultimate proton taker or exchanger or medium of transfer for protons. Okay, that's the end of that little extra tidbit there. Now going back to our regularly scheduled material. Just thought I'd share that with you in case you're interested. That will become a topic later on in more advanced chemistry classes if you continue on. Okay, let's move on now. Here's another place where hydrogen bonding really matters to us. By the way, water, of course, is important to life, and life wouldn't exist if water didn't have its particular dipole-dipole hydrogen bonding properties. But here, this is in our own DNA. DNA, as you know, encodes the instructions for life, all life, not just humans, but all life. DNA is made up of 4 bases: adenine, guanine, cytosine, and thymine. That's what A, T, G, and C stand for. Adenine, thymine, guanine, cytosine. I don't need you to know that, but I'm just letting you know. Now, over here, we have, well, here on the left side, we have the DNA, the ladder of life, right? And we have GCTA. Guanine will only ever attach to cytosine, and adenine, A, will only ever attach to thymine. This is how it works. C never goes with T, G never goes with A. G also never goes with T, and C also never goes with A. I think I said, I'm not sure if I said that already. So this is the DNA helix of life, the double helix of life. It's a helix partly because of the way the molecules themselves wind themselves around. Let's not worry too much about that right now, though. But my point is this. There are 2 reasons for why hydrogen bonding is the most useful type of interaction here, and why This relatively weak bonding compared to covalent bonding is used rather than covalent bonds. You might think, well, DNA is so important. Wouldn't nature pick a much stronger type of interaction like covalent bonding? Remember, even the strongest intermolecular bond is 1/10 or less the strength of a typical covalent bond. Even the weakest covalent bond is 10 times stronger than hydrogen bonding. So these bonds are relatively easy to break. You can break all of these bonds. That ends up being perfect for DNA because what does DNA need to do? Two things which require this DNA molecule, this double helix, to unravel. The DNA molecule needs to unravel. Well, the only way it's going to unravel is if these hydrogen bonds, which are literally the only thing holding these two strands of two different molecules together, if these things can be broken and then reassembled. The hydrogen bonds here act very much like a zipper. When needed, you can open up, you can separate the strands of DNA, break them open, come in, have enzymes, which is just little molecular machinery, come in, make copies of genes to be translated into proteins. So that's one thing, translation, actually technically transcription and then translation to take genes, to take the gene information encoded by the A, Gs, Ts, and Cs, turn them into proteins for our bodies to use. The other thing is to make copies of the DNA molecule itself when you're undergoing well, actually either one, meiosis or mitosis, both of them. When the cell is splitting, when you're dividing up a cell into a new cell, you need to duplicate the copies of DNA. So in order to copy the DNA, you have to break open the DNA, you have to break open the two strands, separate them, copy each one, make a new copy of each one. Whoops. Make a new copy of each one, and you get yourself two new DNA molecules. So that's another thing. So there are two reasons why you don't want DNA covalently bonded together. You don't want those two different helices, those two different bands of molecules completely and permanently bonded together, because you need to translate genes that these things encode for into proteins even while you're alive. And then you also want to make copies of DNA for when your cells multiply or when you're growing or whatever. So that's the reason. So if these were covalent bonds, we'd be dead. We would never exist, in fact, because there would be no way to separate these from each other. Notice they are hydrogen bonds. You have a hydrogen bond. Hydrogen and nitrogen, hydrogen bonding. These are all hydrogen bonding. Nitrogen to hydrogen, nitrogen to hydrogen. Here's another reason, other than that, other than the structural integrity, or actually the fluidity, the flexibility in the structural integrity of DNA. The other reason is this. Notice that it takes 3 hydrogen bonds to link up a C and a G. Cytosine and guanine require 3 H bonds. Thymine and adenine require exactly 2 H bonds. They connect together based on the relative positions and angles of the hydrogens pointing at their corresponding nitrogens or oxygens. One way to avoid making mistakes is this. A guanine cannot attach to a thymine because it has the wrong setup. It has the wrong angles and the wrong atoms on its side. It's like the plugs just don't match. It's like trying to use a European plug on an American outlet. It just won't work out. I don't know if you've ever been to another country, but they have different plugs in different countries, different outlets, different numbers of holes in different ways, different shapes to those holes. So it's trying to use one type of plug on a different kind of outlet. It doesn't work. And so that prevents errors from occurring. That prevents G's from linking up to T's or C's linking up to A's. That simply doesn't happen because it's very specific. And the specificity comes down to the hydrogen bonding. So hydrogen bonding saves us from a bunch of DNA errors. So there are a lot of good reasons why hydrogen bonding is built into our DNA, literally built into our DNA. So you should understand this because you're made of this. I'm kidding, of course. But I do hope you understand this after today. I hope you have a good appreciation of hydrogen bonding. Oh, by the way, just to point this out, phosphate. Do you see the phosphates? You recognize this? This is your polyatomic ion and all this complexity. Do you notice something? There's that phosphate group. This is your polyatomic ion, PO4, 3 minus. Well, you probably can't see the 3 minus. You only see that 1 minus, but the other 3 are there, I assure you. Or actually, it's what's called a phosphate ester or a phosphoester. In any case, phosphate ion, that's one of your polyatomic ions. See, even a molecule as complex as DNA, you can still find some fairly inorganic basic chemistry there. If this molecule, by the way, looks familiar to you at all, think back to a few modules ago. Doesn't this look a lot, it's not exactly the same, but doesn't this look a lot like caffeine? It also looks a lot like theobromine. It's not caffeine. I don't want you to think it is, but it's a very similar backbone. These are called bases, and caffeine itself is a basic molecule. It's a base. Anyway, I just thought I'd show that to you. Our bodies use some very similar molecules to the kinds of things we ingest. Okay, let's move on now. I don't want to make this longer than it needs to be for you. Okay, intermolecular forces and physical properties. So I've already mentioned several times that boiling point is strongly related to intermolecular forces. The stronger the intermolecular force, the higher the boiling point, and if it's a solid, then the higher the melting point. So molecular solids will melt at higher temperatures if they have strong intermolecular properties. In fact, they will be solids if they have strong intermolecular forces. The thing that allows them to be solid to begin with is very strong intermolecular forces. Nonpolar molecules tend not to be solids at room temperature unless they're very big, like plastics and rubbers, which have huge networks of carbons attached to each other in long, long chains, thousands and thousands of atoms large. But for the most part, small nonpolar molecules tend to be gases at room temperature or at best liquids. Okay, so for polar molecules, you're looking for the strength of the dipoles. Hydrogen bonding, of course, is the strongest type. Then you have regular dipole intermolecular forces for quote unquote regular polar molecules. All the kind of stuff we've already talked about before. Another thing I want to relate this to is vapor pressure. Now, it is the exact opposite of boiling point. There's a tendency to think that boiling point and vapor pressure are the same thing because they are related, but not in the way superficially that you might think. You know what vapor pressure is. It's the pressure of the gas phase of a liquid above the liquid. It's the vapor of a liquid, how much pressure it exerts. They are opposites. The harder it is to boil something, the lower its vapor pressure will be. And that makes perfect sense, doesn't it? If it takes a lot of energy to vaporize something so that it boils, then that means at any given temperature before you manage to vaporize it, the vapor pressure must have been low because you must not have been very successful in vaporizing it. So the higher the boiling point, the less success you're going to have at vaporizing something, or the more energy, the more difficult it is to vaporize something. So high boiling point equals low vapor pressure. You're not going to generate, what is boiling point? Boiling point is simply the point at which, the temperature at which the vapor pressure equals the local atmospheric pressure. The normal boiling point is the temperature at which vapor pressure of a liquid equals 1 atmosphere. But any boiling point, the general term, is when the vapor pressure finally reaches the local atmospheric pressure. Well, fewer molecules in the vapor state, you're going to have lower vapor pressure overall for any given range of temperatures. They are very much, they're measuring the same thing. Boiling point and vapor pressure and volatility are measuring the same thing, but they are measuring them from opposite, reverse, reciprocal, inverted points of view. They're looking at the same coin, but boiling point is looking at heads. Vapor pressure and volatility are looking at tails of the same coin. Volatility is just a measure of how easy it is to vaporize something. A liquid that is volatile is one that can easily be transformed into its vapor, into its gas phase, even without boiling, meaning, even at room temperature. For example, acetone, the molecule we looked at earlier, acetone is relatively volatile, meaning if you simply pour some acetone onto a kitchen counter or onto your chemistry counter one day, if you're ever back in the lab, if you just pour a little bit of acetone out onto the counter, within a minute, you can actually watch it happen. The acetone will vaporize. And that's not because you've reached the boiling point of acetone. It's because of that lack of equilibrium we talked about. The equilibrium has to be established, otherwise all the liquid eventually evaporates away. Well, if you don't trap the acetone, it will easily evaporate away because it has a relatively low boiling point, but then even below the boiling point, at any given temperature below the boiling point, it has a high vapor pressure, meaning it quite easily converts into its gas phase from the liquid phase. In fact, if you pour acetone on your hands, and it's perfectly safe, your hands will feel very, very cool. Not cold, they won't freeze or anything, nothing dramatic, but they will cool, they will feel very cold. And that's because acetone will immediately take the heat from your hand and vaporize right away, stealing heat from the surface of your hand, and you'll feel cool. It won't freeze you, don't worry. So example, water has a vapor pressure, and we've mentioned this before in the previous video, 20 millimeters of mercury or 0.026 atmosphere. Look at that very low vapor pressure at 20 degrees Celsius. But you get up to 100 degrees Celsius and that vapor pressure goes up to 760 and 1 atmosphere. So water isn't all that volatile. However, if you leave water out in an open container overnight, you will notice that a lot of the water does evaporate away, depending on the shape of the container and how much, if it's really wide-mouthed and wide open container, yeah, a lot of it will leave. If not, it may take a few days. Water has has a low vapor pressure for any given temperature range, relatively speaking, and a high boiling point because of the strength of its intermolecular forces of attraction. What about acetone? Well, remember, acetone had London forces, but it also had it had a net dipole, but it also had a fair amount of London force. Because it had those two methyl groups on either side, the dipole was there, but it really wasn't the only part of the molecule. A good portion of that molecule just didn't have any dipole associated with it. So because of that, acetone's intermolecular force overall is kind of weak. And because of that, it vaporizes relatively easily. Still above, and it still boils above room temperature, but it's still kind of weak. So generally, all else being equal, substances with higher intermolecular forces tend to be also more dense. That's because they crowd together. If you've ever noticed, oil always floats on top of water. Despite the fact that oils seem very, very viscous, very thick, they might seem like they're more dense, but they're not. Oils are, generally speaking, pure hydrocarbons, especially the kinds that unfortunately leak so often in the ocean and the bay. Like right now, we've got a big oil leak out in the ocean. So because of that, actually and I don't even have to worry about that being linked to some kind of period of time. I could say this at any point. There's an oil leak right now burning in the ocean. And you know what? The sad thing is that applies all the time. We could be talking 5 years from now. You could be listening to this video and it'll still be true because it's always true. We're never going to learn. It's never going to be safe. It's never going to be risk-proof. Okay, anyway, oils are basically hydrocarbons. Hydrocarbons have relatively low density compared to water because of their relatively low intermolecular forces. They don't crowd together that well. There are other reasons that are beyond the scope of this class when it comes to organic compounds like hydrocarbons and the amount of branching in those carbons and how much they overlap with each other. But for now, just take my word for it. A big part of the reason that oils float on water is because they are nonpolar. So they don't crowd together. They're not attracted to each other. So they sort of float around. Water, on the other hand, it's a small molecule, and water molecules really stick together very well. In fact, so well that the liquid phase of water is actually more dense than the solid phase. That's very unusual. And I've yet to hear back from anyone, I think, who can name another compound where that's true. There is another one. Okay, so that's why water tends to be on the bottom, oil tends to float on top. And that's generally true of any hydrogen bonding molecule. In the liquid phase, the hydrogen bonding molecule or substance will be on the bottom, and the hydrocarbons will be on top. So if you look at vinaigrette dressing, for example, a salad dressing, oftentimes it's a mixture of vinegar, acetic acid, which has hydrogen bonding, versus oils. The oils are always settled on the bottom. There are two layers. The vinegar floats on top of the oil, again, because the oil, reverse that. The oils tend to float on top of the vinegar. The vinegar sits on the bottom because of the hydrogen bonding. It tends to be more dense. The oils float on top of the vinegar because they are less dense, being hydrocarbons. Okay, comparing the expected physical properties of molecules. Compare ethane and methanol. Methanol is it's a smaller version of acetone without all the extra carbons. I picked these two for a reason. You'll see in a moment why I chose to compare these two. In terms of their boiling point and volatility, when I say volatility is best measured as the vapor pressure across a given temperature. In other words, we can just say in general, does this molecule have a higher vapor pressure or a lower vapor pressure? Okay, so first, let's determine which molecule will have the stronger intermolecular force or which one will have the weaker one. So comparing these, let's take a look. Let's draw them out. For example, C2H6. Well, you don't even really need to know, right? You can already see this is a hydrocarbon. Therefore, hydrocarbon, nonpolar, therefore, London dispersion. And it's relatively lightweight. It has a 30 gram per mole molar mass. How about the other one? Yeah, let me draw this out for you, just in case you have trouble from the structure up there. Although I hope you don't, because this is one of those molecules you can draw, and in fact, you have drawn the Lewis-Dot structure for it. Trigonal planar, you've got yourself a dipole, no hydrogen bonding, but you do have a dipole, a pretty good strong one too, because most of the molecule is composed of the atoms that make up this dipole. So it's dipole-dipole intermolecular forces. So what's the molar mass? Well, we've got 2 plus 12 plus 16, what do you know? 30 grams per mole. So they both have exactly the same molar mass. London, for the same given molar mass, London is always weaker than dipole-dipole. So London, let's see, what do we say? Compare them in terms of their boiling point and volatility. Okay, so given that this is London dispersion, this one's dipole-dipole, and they have the same molar mass, this one will have a far lower boiling point and melting point. P for boiling point, MP for melting point, lower boiling point and melting point, higher volatility, meaning higher vapor pressure at any comparable or any given temperature that you choose to compare these two molecules at. So say, for example, at room temperature, if you're comparing them both at room temperature, C2H6, so-called ethane, will have the lower boiling point and melting point, but higher volatility and higher vapor pressure. So that, of course, if it stands to reason, if this is higher, this one is lower, this is the opposite. This is high boiling point, relatively speaking, high boiling point, high melting point, and low volatility, lower than the other one, compared to the other molecule, low volatility, low vapor pressure at comparable temperatures to the other one. Why? Because these are going to stick together. The C double bond O here, and let me just write this in a sort of compact fashion so we can see them compared to each other. These dipoles are going to connect to one another. The opposite partial charges are going to be interested in one another. They're going to connect like Velcro. And so they're going to stick together, which means they're going to stay in the liquid phase a lot more strongly, a lot more tightly, and you're going to have to provide a lot more energy in order to separate them, in order to excite them into their gas phase. In order to give them enough energy to overcome their own intermolecular forces of attraction, you have to give them a significant amount of energy, meaning you have to raise their temperature quite a bit with enough thermal energy. Second, relate the strength of the intermolecular force to the boiling point. Well, we know that London dispersion forces result in lower boiling points and melting points. Third, recall that vapor pressure is inversely related to boiling point. So low boiling point, high vapor pressure, high volatility. Vapor pressure and high volatility are basically saying the same thing. They're measuring the tendency of a liquid to become a gas, to enter the gas phase. Okay, another example. Which of the following molecules has the lowest boiling point? So same kind of thing. Go through, look for the types of intermolecular forces. A, we have London. Definitely. Its formula is C6Hy, meaning it's nonpolar, meaning because it's a hydrocarbon, meaning London. In fact, here, let me just put that little train of thought right there. Let me write this a little more clearly for you. So HXCY means it's a hydrocarbon, means it is nonpolar, and therefore means you have London. This train of thought never derails. Anytime you see carbon, hydrogen, those are the only two atoms or elements in the molecule, the thought process does not fail. In fact, we can say the exact same thing for the next one. I feel like we've done this already. No, we have not. We haven't. This is a little bit different. In fact, this holds true for all of them. They are all London dispersion force except for letter D. What's wrong with letter D? Which one of these things is not like the others? Carbon has a fluorine attached to it. The rest of the molecule is exactly the same except for this. Now, we could say that we could look at molar mass and say, well, this is over 100 grams per mole, whereas this is still well under 100 grams per mole, except for one thing. We've got a dipole. This is a dipole interaction. So regardless of what we want to conclude, there's one thing we know for sure, that there's no way a dipole-dipole molecule compared to a bunch of tiny little nonpolar molecules is ever going to have a lower boiling point. So this is out. Dipole-dipole kind of eliminates. Now, if it were a question between these two and you didn't have options A and B, it would be legitimately ambiguous. Comparison between C and D is legitimately ambiguous. If I wasn't asking for the lowest boiling point and giving you some clearly low boiling hydrocarbons, this would be tough to figure out, and it would kind of be guesswork. It wouldn't be a fair question, to be honest with you. Okay, but that's not the question. The question is the lowest boiling point. Well, that's easy. Now we can, first of all, eliminate dipole-dipole. So that gives us A, B, and C. Well, which one? If we're looking for lowest boiling point, thus we're looking for the weakest of the London dispersion force. They're all London, right? They're all London. So we're looking for the weakest of the Londons. Well, which one is the weakest? The one with the lowest molar mass. The one with the lowest molecular weight or molar mass, same term. I use them interchangeably. I think you've noticed that by now. The one with the lowest molar mass. Well, that's clearly A. C2H6, that's only 30 grams per mole. All the other ones, C3H8, are going to be higher. That's 44 grams per mole. Octane, as you can clearly see, is going to be over 100 grams per mole. So I think we can pretty much rule out the heavier ones. The lightest one is the one. lowest molar mass, therefore the weakest London dispersion force. London dispersion force is weaker than dipole-dipole, therefore the weakest London is the weakest intermolecular force, which gives rise to the lowest boiling point. Had I asked you for the highest boiling point, it would have been very difficult. In fact, you would have only had to be able to, you could only take an educated guess about the difference between these two. I would guess octane only because it's so much heavier, so much heavier. Remember, even heptane with one less carbon had a comparable intermolecular force to water, which is far more polar than fluoromethane. This is fluoromethane. So I would say C, that would be my guess. If we were looking for the highest boiling point, but we're not, we're looking for the lowest boiling point. So that makes this a lot easier, it's A. Which of the following, here's another example. This one I've actually written out the explanations and answers for you so that you can look at it at another time without watching till the end of the video. Which of the following molecules has the lowest boiling point? Again, another low boiling point one. Sadly, oh wait, this is the same problem. All I did was write out the answers and write out the explanation. Oh, well, I did do that so you wouldn't have to watch the entire video to the end to see this example, but there it is for you. Okay, so that's the actual explanation written out for you, available to you anytime. It seemed to have gotten some of this cut off here. Now let's talk about another physical property other than boiling point and melting point or even density, solubility, or what's called, when you're talking about liquids, dissolving or making solutions with other liquids, specifically, we use the term miscible or miscibility, M-I-S-C-I-B-L-E. Miscible just means mixable. It means exactly the same thing, just say miscible. Okay, so this term is a good term to remember. Like dissolves like. In other words, two liquids with the same types of intermolecular forces are going to dissolve one another. They're going to mutually dissolve each other. They're going to form a homogeneous mixture, meaning a true solution. They're not simply going to, unlike oil and water, where you simply have two liquids that happen to be in close proximity but don't form a true mixture because they separate into their own phases and you can see them separate out. Two liquids that have similar intermolecular forces will actually form a true mixture where there is no barrier between the liquids. They are completely intermixed. So two polar compounds will mix well. So that's what like means. Two polar compounds will mix well, or like meaning two non-polar molecules will mix well with each other. Like just refers to the type of intermolecular force. Polar does not mix with non-polar. Polar mixes with polar, non-polar mixes with non-polar, but non-polar does not mix with polar. That's what it really means. In this case, opposites do not attract. Okay. So again, we have the same old thing. Oil and water don't mix, or oil and vinegar. Another way of saying it, by the way, is oil and vinegar don't mix, because vinegar is also loaded with a bunch of dipoles, and vinegar don't mix. Remember, look back at the structure of vinegar in that example we looked at earlier, a few slides ago. Vinegar is loaded with intermolecular dipoles. It has regular dipole, and it has hydrogen bonding dipoles. So it's got plenty to offer another polar molecule. What it doesn't offer is a sort of a docking point for any kind of non-polar molecules. The reason this happens is because basically polar molecules will crowd out all the non-polar molecules. Because the polar molecules are so attracted to one another because of their dipoles, they will squeeze together and they will squeeze out those very weak intermolecular molecules, the non-polar molecules, because they have nothing to offer. They have no strong dipoles. So they squeeze them out. So the active exclusion is really what's going on here. That's how the so-called phase separation between polar and non-polar occurs. The polar molecules all squeeze together and sink to the bottom. The non-polar molecules are left out to hang around one another and float on top. Not because they like each other, but simply because they didn't have enough attraction to stick with the polar molecules. It's all very cliquish at the molecular level. Just a bunch of groups Just a bunch of tribalism. Okay. So vinegar is also very polar. Substances with dissimilar intermolecular forces do not mix together. In their liquid phases, they are called immiscible. By the way, immiscible, the im here is like the prefix un. They're unmixable, unmixable. Two dissimilar types of intermolecular forces are unmixable. We say they are immiscible. Don't confuse these words. They sound a lot alike, and I've noticed some confusion in the past. Miscible means mixable. Immiscible means not mixable. Think of it as inmixable if you prefer. It's not a spelling contest, so if you ever write it as immiscible, that's fine. That's totally admissible as far as I'm concerned. Oh, and I mentioned the oil spills thing here. I already mentioned that to you. So you can read that here. Good thing that's the part I got cut off. I've already talked about it. Oil spills, of course, the oil floats on top of the salt water. By the way, salt water is even more dense, slightly more dense than pure water because you have the extra added mass of the salt, of the sodium chloride and other compounds dissolved in the water. Makes it a little bit heavier per milliliter. So there's also that. In addition to the fact that water itself, pure water, is also already more dense than hydrocarbons, you also have salt water, which is even more dense than regular water, pure water. Okay, one more example. This time I really mean an example we can walk through together. Which of the following would be soluble, in other words, miscible, and I'm going to use the word miscible from now on, but soluble or miscible with hexane. And here's the formula for hexane, liquid hexane. This is a liquid at room temperature. So we have liquid hexane. What kind of molecule is this? It's only got carbons and hydrogens in it. Therefore, it is a hydrocarbon. Therefore, it is nonpolar. Therefore, its type of intermolecular force is London. Okay, so which of the following would be soluble? So we're looking for other London dispersion force molecules. In other words, we're looking for other nonpolar molecules. So A, B, C, and D, are they polar or nonpolar? Let's take a look. Carbon disulfide. I'm going to quickly draw you the structure, but you should be able to draw the structure yourself correctly. Carbon disulfide is a linear molecule, and the bonds themselves are very low in polarity, but on top of it, it's a totally nonpolar molecule simply because even if these were very polar bonds, they would cancel out because it's linear and you have exactly the same atoms on either side with no lone pairs in the center. In other words, it's a very symmetric shape. Even if it had dipoles, significant dipoles, they would cancel. One would point left, one would point right. So this is nonpolar. Therefore, A is definitely going to be a liquid. Carbon disulfide is a liquid. It smells like rotting cabbage, and it's toxic to your brain. So if you're smelling it, stop. Anyway, carbon disulfide is a liquid. It will mix well, or at least it's predicted to mix well with hexane because they are both nonpolar. They both have London dispersion forces. How about carbon tetraiodide? Well, if you draw the structure, you end up, whoops, that's a sideways iodine. That's all I really meant, right? Iodine, iodine, iodine. We have iodine over here. So we have a very non-polar molecule. We have the same atom and no lone pairs on the central atom. We have a very symmetric atom. Even though there are definitely dipoles here, all the dipoles will cancel each other out. Remember, there's going to be a net dipole pointing between these two iodines and a net dipole between those two iodines, and they're going to cancel. So all dipoles cancel. This is nonpolar, and therefore London. So B will also be miscible with this nonpolar hydrocarbon hexane. How about methanoic acid? By the way, as soon as you see noic acid, as soon as you see that, that is a sign that you're dealing with something with this sort of grouping attached to it. Whatever the rest of the molecule is doesn't even matter. Look at this molecule. You've got a dipole, you've got hydrogen bonding. This molecule is pure dipole in every direction. There's no way something like this is going to mix with a polar molecule. All the methanoic acid molecules are going to crowd around with each other, and they're going to completely exclude all the hexane. And because they are so attracted to one another, they're going to squeeze together a lot of mass in a little bit of space to make them very dense. So this is definitely out. Dipole, dipole, I'm just going to write, well, here, dipole, dipole, dip, dip, if you prefer, and hydrogen bonding. You've got both of the strongest types of intermolecular forces, definitely not going to mix well or be miscible with the very nonpolar hexane. Finally, you have calcium chloride. Calcium chloride is an ionic compound. Now you might say, well, that's the ultimate then, isn't it? The ultimate dipole. It's not a dipole, but it's true that there is nothing that hexane has to offer in order to steal away the negative charge away from the positive charge. So no ionic compound is going to dissolve in a nonpolar solvent. This is, by the way, would be a solid. This is the only one that's a solid. So technically, it wouldn't even be miscible. It would be, if it could dissolve, it would be soluble, but it will not dissolve either. So it will definitely not dissolve because there are absolutely no dipoles in hexane that can pull apart the negative charge, that can attract the negative charges of the chlorides away from the positive charge of the calcium, and vice versa, to attract the positive charge of calcium away from those negative charges of chloride. Nothing will do that. Hexane's got nothing to offer calcium chloride. So it will remain a solid linked together. Now, water, on the other hand, can do that. Water's dipoles, at least with enough water molecules, and it takes several, it takes probably a dozen or more water molecules to do this, but enough dipoles from water will steal away the ions, will separate the ions of an ionic compound from one another. Let's take a look at that. Summary of things to know so far. I'll let you read this on your own, but I want you to know, well, I guess we'll read it together. Be able to identify the main types of intermolecular forces in a substance just by looking either at its formula, or if you're not familiar with the structure, or looking at the structure if I provide it. I will not provide structures for things I expect you to know. So for like methane or CF2H2 or something like that, something with a central atom and multiple atoms around it, those you already know how to draw, so I want you to draw those. But anything else, I will always provide the molecule for you. Sometimes I'll do it anyway, just for whatever reason, but make sure you know you haven't forgotten your molecular geometry and your polarity, determining polarity from molecular geometry. This is where you really are going to apply that some more. Predict the physical properties, or at least be able to at least expect some physical properties of a substance: melting point, boiling point, vapor pressure, density, volatility, and miscibility, solubility as well. Predict whether two or more liquid substances are miscible, meaning mixable, based on the types of intermolecular forces and whether they are polar or nonpolar. Really, polar goes with polar, nonpolar goes with nonpolar. You don't even have to analyze the intermolecular forces that much. If you can just distinguish between polar and nonpolar, I mean, stuff you learned back when we were talking about this earlier on in an earlier module, you'll already know the answer to that. Okay, let's talk about the ion-dipole interaction. This is the only interaction that I listed at the beginning that we have not spoken of yet. In many ways, this is the simplest one because there's only one situation the ion-dipole ever takes effect. It's when you have an ionic compound mixing with the dipole of a molecular compound. When do you see ionic compounds and molecular compounds interacting with one another? Only one situation, when you take a solid ionic compound and dissolve it in water. Yeah, you can dissolve it in alcohol too. That would also work. But for the most part, we make aqueous solutions with water. We don't typically try to dissolve them in anything else, any other polar molecules. So it always, always, always involves an ionic compound dissolving in water. Look for those, it has to be both of those things. Otherwise, it's not the ion dipole. It's simply electrostatic. What holds the ion? Electrostatic interaction. Remember that word. That just means positive ions and negative ions. The molecular compound known as water, on the other hand, is held together. Well, the molecule itself is covalent, of course, but it is polar covalent. The dipoles of water are going to lead to them. Well, actually, this picture puts it a little bit better. Do you see how you have a negative charge on the chlorine here? Well, the water has positive ends. Its hydrogen has that partial positive charge. I don't know if I can zoom in here a little bit for you. Oh, sure, now that I want it to work. Here we are. Okay, so you notice how you have the positive on the hydrogens. Those positive ends of the dipole on water that's the dipole they're going to interact with only the negative ion from sodium chloride. Likewise, the negative end on the water molecules where the oxygen is going to interact with only the positive sodium ion. Thus, you can take a solid, and it will be dissociated. It will be broken up into its individual ions, and those ions will be spread amongst a bunch of water molecules, dozens of water molecules. It takes dozens of water molecules. Don't look at this picture. It takes more water molecules than even shown here to separate, to draw away one negative charge from one positive charge. But once it's done, these negative ions, instead of being clumped together, will be spread throughout the entire liquid region of water. They will be evenly, uniformly distributed into an aqueous solution. So if a solid ionic compound dissolves in water, you have created a true solution. It is dissolved. It's not simply sitting in the water the way this white powder is. By the way, this white powder probably isn't salt. Or if it is, it's because this is what's called a supersaturated, actually technically a saturated solution. Maybe it's supersaturated, but you can't tell just by looking at it yet. Okay, so the dipoles in water effectively gang up on ions and pull them apart from each other. The blue wedges will represent water. Well, I don't think you can see any blue wedges here. I'm just going to cross that out for now. Don't worry about blue wedges. I have better pictures now than I used to, so maybe I think that's what the issue is. I think I'm describing a worse picture, probably one that I drew. The strength of the electrostatic interactions is the main reason you probably have never seen molten salt. There's a big difference between dissolving salt in water, which is one phase of matter, and melting salt into a liquid, which is a completely different phase of matter. Salt technically melts at 800 degrees Celsius. That's hotter than any home oven can get. You've probably never even seen that though, because even that is hard to achieve, because in order to get the salt to that temperature, you also have to trap the heat rather than letting the salt sort of transmit or conduct that heat to the air around it. Remember, it's not enough just to try and get something to get a flame up to that temperature and apply it to whatever you want to melt. You have to trap the heat so that the heat isn't conducted through convection or through conduction or through irradiation, which is the least likely method, somewhere else outside of the substance that you're trying to heat up. So practically, for practical purposes, even this probably isn't enough to melt salt, unless you've got a kiln or some kind of special device that prevents the heat from escaping too much, that allows heat to the flame if you're using flame, but doesn't allow the heat to escape to the air outside. So ionic compounds have extremely high melting points. So dissolving takes a lot of energy to separate a positive from a negative. That's because water is equipped with its own partial charges to do so. Here's an analogy I like to imagine. All these little water molecules trying to pull apart a chloride from a sodium is sort of like having a bunch of little children trying to pull two adults apart from each other who are fighting. The little children are weak, but if you get enough of those little kids, they'll pull two grown, strong adults apart from each other if they can gang up on them. So that's kind of what's going on here. Individual water dipoles are very weak, but if you get enough water dipoles to surround, and of course you need enough space and distance to surround these ions, you can get them to attract and sort of almost like distract the negative ions from the positive and the positive from the negative. They're basically saying, hey, look over here, forget about that sodium. And they're saying telling the sodium, hey, look over here, forget about that chloride. We've got all the negative charge you could ever want. Hang out with us. So that's the idea. So that's the ion-dipole interaction. It is only for dissolving ionic compounds in some sort of polar solvent. 99.9% of the time, that solvent is water. Here's some other stuff I want you to take a look at. I want you to know this terminology. Surface tension. You've seen surface tension before. You've seen bugs walk on water without sinking. You've seen astronauts hold up globs of water in the space station, and it looks sort of spherical. That's surface tension is the tendency of a liquid to minimize its surface area to reduce contact with air or any other substance that's dissimilar to its intermolecular forces of attraction. In other words, water, for example, if you take water as the example, water molecules want to be with other water molecules. They don't want to interact with the air because think about what our air is made of. Mostly non-polar molecules like O2, N2, and argon. Because of that, water molecules are attracted to other dipoles like themselves. So they don't really want to waste their time being stuck away from their fellow molecules. Their dipoles need opposite charges, opposite partial charges to balance them out. So water molecules will sort of bead up or ball up, turn into little spheres to minimize that surface area. The way to minimize surface area to volume is to create a sphere. A sphere has the minimum amount of surface area to the maximum amount of volume. So water outside or absent the influence of gravity will form spheres of water, like for example on the space station. Or if under the influence of gravity, even flat water in a pool or in a puddle will form a sort of skin on the very surface. That's because the molecules of water on the surface of the water are holding extra tightly to one another because their bonds are just sort of being unfulfilled. They have these dipoles, these raw negative and positive charges that have nowhere else to go but to touch each other sideways, laterally. Because they're missing an entire layer of water molecules above them, because there's nothing but air, they will instead they'll be attracted more to their fellow molecules side by side, and that will create a sort of scaffolding or skin on the layer of water. That's why bugs can walk on water. Generally, the stronger the intermolecular forces of a liquid, the greater the surface tension. Mercury, for example, liquid mercury has such a high surface tension, it actually will bead, B-E-A-D as in David, bead up, and actually will form the opposite of a meniscus. It'll actually form a meniscus, a maxiscus, I don't know. They'll form a concave surface when placed into a tube because the mercury does not want to interact with the tube. Water will interact with the tube because of the cohesive forces. The water is attracted to glass because they are both polar substances. But mercury enjoys something called metallic bonding. And because of that, because no glass or plastic has similar metallic bonding, mercury will actually bead up and it will form a sort of spherical puckered surface when you put it into a tube. It'll actually move up, it'll actually round up instead of rounding into a meniscus. That's because mercury has extremely strong intermolecular forces because it engages in something called metallic bonding, which is altogether different from the molecular forces we've talked about so far. We will talk about that, but not just yet. Viscosity is the liquid's resistance to being poured or to flowing. And you can think of viscous. The term viscous means a liquid that has high viscosity. Inviscid is the opposite of viscous. This is kind of strange here, and I know that, but inviscid means flowing very freely. Viscous means not flowing very freely. They sound like they should be opposites, but they're not. Inviscid is the opposite of viscous. So you've seen syrup, molasses, motor oil, lava, which is just liquid rock, liquefied rock. These all have very high viscosity. They are all very viscous liquids. Generally speaking, the stronger the intermolecular forces, the more viscous a liquid will be. Now, water seems to be a very obvious contradiction to that rule. Water has a very high intermolecular force, but it flows extremely easily and extremely quickly. I can only attribute that to the fact that water also is a very small molecule. Other molecules that are larger and have lower intermolecular forces actually do flow a lot slower. Like motor oil, for example, is mainly made up of hydrocarbons. And they tend to be middle range, like 5 to 10 carbon long hydrocarbons. By the way, the formulation of gasoline changes by season. This is a little bit of fact that may help you to understand this concept. In wintertime, shorter chain hydrocarbons are used in fuel mixtures. When you go to the gas pump in winter, you are getting different gas from the kind of gas you get in summer. In winter, they use shorter chains because they are less viscous. The gasoline flows better if the chains of the carbons are shorter, meaning you have less than 10 carbons. In winter, that's because the low temperatures in winter cause the gas to slow down. Remember, colder temperatures slow down molecules. Those slower molecules will attract each other better. They are more likely to liquefy, not liquefy. If they're already liquids, they're more likely to move more sluggishly. On the other hand, in summertime, you don't want your gasoline to vaporize in the hot temperatures. So they use longer chain, higher London dispersion forces. Longer chains of carbons means more molar mass. So because of that, you get higher boiling, lower vapor pressures in your gas tank because of that, because they used longer, bigger hydrocarbons for your fuel mixture. So you may not know it, but seasonally, your gasoline does change. And that will actually impact your gas mileage. Different fuels, different fossil fuels have different energy densities per gram, meaning some fuels will burn to produce more energy than others on a per gram basis, or they'll even have different densities. So even on a per gallon basis, you might get a different energy pack. So I don't know the relative energy densities of the different fuels, but you may find that at different points during the year, you'll get a different fuel economy because of that, because they're using different mixtures of gas. And they're not trying to rip you, well, they're always trying to rip you off. But in this way, it's not because they're trying to rip you off. It's actually more of a liquid flow engineering kind of consideration. I'm sure they're getting us somehow, though. All right, we talked about volatility already. Sublimation, we've talked about that before, but just as a reminder, sublimation is changing phase directly from the solid state to the gas state without passing through a liquid state. Dry ice, solid carbon dioxide sublimes or sublimates. It goes directly from the solid state to the gaseous state without ever becoming liquid carbon dioxide, at least not at the pressures that we deal with here on the surface of the Earth. What else does iodine? Iodine also goes directly. When you heat up iodine, it starts off as a gunmetal gray solid. If you heat it up to about 50 or 60 degrees Celsius, it turns into a beautiful purple vapor. It doesn't liquefy. In fact, it'd be very difficult for you to capture liquid iodine. It's actually, I've heard that it's technically possible if you're very, very careful, but I have not seen it, and I have sublimated iodine many times. So I'll leave that to you. So sublimation, going from gas to liquid, from the solid to the gas phase, no liquid phase, not passing through a liquid phase. Deposition is the exact opposite of sublimation. It's going directly from the gas phase right back into the solid phase without passing through a liquid phase. Oftentimes this is used for coating things. If you want to coat, for example, if you want to coat some sort of plastics or some sort of glass rod or glass panel with ceramics or with maybe some sort of silica, you will, or metal coat something like an electrode, you will deposit it. You will take the gas, you'll get the gas phase of the metal or the substance, put in the thing you want to coat, and then just let it sort of deposit, re-crystallize, re-solidify onto the surface of that, of whatever it is you're trying to coat, whatever coating you need. Condensation, you may not have heard this too often, although I know you've heard of it. It's going from the gas phase to the liquid phase. It's the exact opposite of vaporization or evaporation. Condensation is the opposite direction. Gas phase into liquid phase. It's liquefaction. Liquefying. That's what it means. Condensation is the liquefying of a vapor. And of course, the vapor is just the gas phase of a substance. So liquefying or condensation. If you've ever seen beads of water form on the outside of a cold cup on a hot day, that's not the water coming from inside the cup. That's the moisture in the air hitting the cold cup and condensing. You're getting condensation from the moisture in the air. It's liquefying. It was In the air, it was hot enough that the H2O it remained in the gas phase in the air, but as soon as it touched that cold surface, the water molecules liquefied. They coalesced into a liquid rather than into a vapor. Here we have types of solids. Now, I'm just going to go through this a little bit quickly, and I'm mainly just going to show you pretty pictures. And I think the picture, and that's intentional because the concept is a lot more easily transmitted via picture. In this case, a picture really is worth 1,000 words, number one. Number two, we're not going to really go deep into this. You can go very deep into the different arrangements of solids. This is only going to scratch the surface. I just want you to have a picture in your mind of what solids can look like, of how at the atomic level or the molecular level, how solids actually arrange themselves. That's it. I just want you to have this picture in your head. You know, if you need something to help your imagination, that's all it really is. Okay, types of solids. There are two general categories, but really for the most part, we're going to ignore the amorphous or the glassy state. Amorphous means without structure, without shape. A means without, morpheus means shape, morphous. So amorphous means something without shape, or the glassy. Sometimes you'll hear it as the glassy state. This is basically a sort of solidified liquid state. There's no order or arrangement to anything. This is a genuine state of matter, or I should say type of arrangement of matter, or solid state, but it's not really one that's going to matter too much to us, okay, or to you either in the future. So I'll just say there's no structure, just a jumble of molecules or atoms together, almost like a liquid, but like a liquid that has solidified before its components have had time to arrange themselves in the lowest energy, most stable possible arrangement. An amorphous solid is very much like a very, very, very viscous liquid, a very slow moving liquid. And it's often been said that glass itself is basically just an amorphous solid, and that it is actually in the liquid phase. It's simply flowing very slowly. And one of the pieces of evidence for this, and I'm not sure I really believe this or if this is urban legend, but the stained glass windows of certain very old churches that are like 1,000 years old or hundreds of years old, the stained glass windows have actually drifted downward, meaning more mass. They've gotten thicker on the bottom than on top. They are essentially slowly melting because they are actually liquid, not melting, actually, they're in the liquid state and they are slowly flowing downwards. I don't know if I believe that's true or not. I don't know, I'd have to see it myself and I haven't really looked into it. Anyway, that's the amorphous idea. There are far more, or it's more common to look at the crystalline, the crystalline type of solid, which has definite arrangement and a definite organization. There are different kinds of solids in the crystalline state. Ionic compounds, and we've mentioned this before, ionic compounds form lattices, a repeating array of a pattern of positive and negative charged ions, where usually the positive ions inhabit the holes or the interstitial spaces between the usually bigger negative ions. Here's another thing though, molecular compounds also form lattices, crystalline lattices. But instead of having ions located at regular intervals, you have the same molecule occupying those individual corners and spaces in a repeating pattern. And we're going to see pictures, don't worry. Ionic compounds, remember, have extremely high melting and boiling points due to the strength of the electrostatic interactions. They have full ion charges, not just these partial charges. Molecular compounds, they come together in the solid crystalline state, not because of opposite charges. What holds positives and negatives together are their opposite charges. They stay in those crystalline lattices because of that. What holds molecular compounds, though, are their types of intermolecular forces. What keeps a sugar molecule bonded to another sugar molecule in a crystal lattice are their intermolecular forces, their hydrogen bonds, their dipole-dipole interactions, their London dispersion forces. All of that keeps them stuck together in the solid state. Without that, they would not be in the solid state, they'd be in the gas state. atomic solids. Now remember, there's only one type of intermolecular force that an atom, a single atom can have, and that's the London dispersion force. So the only thing you're going to get from atomic solids are extremely weak forces, meaning these atomic solids have a real tendency to vaporize. In fact, an atomic solid is something like a noble gas in the solid state. Well, how often do you see a noble gas in the solid state? Well, never, right? I mean, unless you're looking at a small sample inside of a very large cold machine, you probably will never see anything, maybe xenon. But other than xenon, you will probably never see a noble gas in its solid state. It's always going to be in the gas phase. That's because they have as atoms, they have only a very, very weak type of London dispersion force because they don't have much molecular weight because they're single atoms. So when they do form solids, though, they actually, again, they form close packed structures. They pack together just like the ions in a crystal lattice, just like the molecules in the molecular crystalline lattice. They will form these close packed structures that we've looked at before. Only the thing that will bind them together, these atoms together, will be their extremely weak London dispersion forces. And those lattices will be quickly destroyed with even the tiniest amount of thermal energy. 4 kelvins or higher, right? Helium had a boiling point of 4 kelvins. Network covalent solids. These are actually very different from other kinds of solids. They do form an organized arrangement, but instead of individual molecules or individual discrete molecules, they are covalent, right? You would think, oh, they are discrete molecules. They are not. Actually, they tend to form gigantic molecules. When you look at a diamond or you look at graphite, or graphene is a single layer of graphite, when you look at these materials, they are actually extremely large molecules. When it says network covalent, it doesn't mean individual covalent compounds all stuck together based on their intermolecular forces. No, the binding force here is not intermolecular forces. With network covalent solids, the entire solid is joined together by covalent bonds. It's an extended network of covalent bonds. Now, that is a little bit different from graphite. Graphite does have an extended network of covalent bonds. Or actually, I should say graphene is an extended network of covalent bonds. Graphite is too, but the layers of graphite, the layers of graphene that make up graphite are actually held together by intermolecular forces. Nevertheless, each layer is an extended network of millions upon millions of carbons, all joined together by covalent bonds. Finally, we have metallic bonding. Metallic bonding is distinct and completely different from all the other kinds. It's the sea of electrons model of metallic bonding. There's actually a more sophisticated model of looking at metallic bonding called bands, but we're not going to look at that. And we're just barely going to scratch the surface of metallic bonding here, just very briefly with some pictures. So let's take a look at each one of these. Pictures say everything, right? Here's an ionic lattice. So you've seen a picture just like this before in an earlier module. In this case, I don't really like this picture that much, so why did I pick it? I don't know. I like the picture I chose for you. In fact, actually, you know what? This is a much better picture. This is the same idea. We see this here as we have a lattice here. The negative charges are all stacked together. In between the negative charges, the holes or the spaces between that naturally arise between packing spheres, there are these interstitial spaces. That's usually where the tiny little positive cations fit. Remember, cations tend to be smaller because they've lost an entire layer of electrons. So the interstitial spaces are where the cations fit. Overall, the positives and negatives balance each other out. That's why the negative charges aren't exploding and repelling each other, and why the positive charges likewise aren't exploding each other outwards, because overall there's a balance of charges. So this is a crystalline lattice. It's a repeating array of negative charges with positive charges interspersed in between. This is supposed to represent the same thing, but in this case, it actually kind of represents the positive and negative charges almost equally, which I don't particularly like because they often are very different. Now, it is possible to have a crystallized ionic lattice where the cations and anions are almost the same size, but that's not the usual. That's not the norm. Anyway, I just thought I'd show that to you, though. But it is this sort of arrangement. In fact, there's something called A unit square, as you keep going in all directions, the X, Y, and Z directions, the unit square simply repeats with every single corner of the unit square holding exactly the same ion, and the arrangement being exactly the same as you keep going and extending out this network all along the way. You keep extending that same unit square out in all three directions, the unit square. All right. Network covalent. Network covalent. So for example, a diamond and graphite are both made of the same thing. They are both carbon. That's it. That's the entire formula of diamond. It's carbon. It's solid carbon. And graphite is also solid carbon. Amazingly, these two different, what are called allotropes of carbon, allotropes are just different forms of the same element, but it's arranged differently. In the case of diamond, you have tetrahedral. You have tetrahedral carbons all bonded to each other. Instead of having hydrogen, each carbon is bonded to 4 more carbons. Instead of having hydrogens like methane or something, you have carbon bonded to 4 more carbons, and on and on and on, forever outward and outward and outward until you reach the end of the diamond. It's like one gigantic molecule. Graphite has a similar idea. So allotropes are just different forms of the same. So graphite and diamond are just different allotropes, different arrangements of carbon atoms, but they're both just elemental carbon. Here in graphite, you have layers of graphite. The layers of graphite are actually arranged with partial double bonds, partial single bonds, and they're arranged in a sort of hexagonal shape, but a continuous sheet of hexagonal shapes. Whoops, sorry about that. And on forever. Well, you know, not forever, of course, as big as your pencil lead is, or whatever it is that you have graphite for, or your graphene sheet. So it's layers and layers of these hexagonal carbons that are partially singly bonded, partially doubly bonded. The layers themselves are attracted to each other and maintained together through London dispersion forces, though. This is one of the reasons why you can draw with pencil lead, because as you move your pencil across a surface, you are depositing many thousands of layers of this carbon. Every time you draw a letter, it's actually thousands of layers of these carbon or these graphite sheets thick that you're depositing. And the reason they're coming across is because it's very easy to break the bonds in between these layers, because they're nothing more than London dispersion forces holding them together. Silicon dioxide, this is quartz. Sometimes quartz, sometimes glass, depending on the arrangement. This is quartz. Anyway, silicon dioxide. So this is another extended network. Again, you can see that sort of tetrahedral arrangement, and you have just covalent bonds just going on and on and on for the entire volume of the compound. It just continues on. And silicon carbide is another type of network solid. Again, just another version of the same kind of thing. Down here, by the way, if you can make sheets, these are a single sheet of graphite is called graphene. Graphene is supposed to be one of these wonder materials. It's exactly the same as graphite, only it's been separated from all the other layers. You can take graphene sheets and you can roll them up like a newspaper, and you can create something called nanotubes, which have their own type of physical properties and electrical properties. Or you can take another version of carbon called the buckyball. This is called Buckminster fullerene. This is another allotrope of carbon. It's pure carbon. Every point along here is carbon. It's shaped exactly like a soccer ball. It's got 5 and 6 membered rings. Just like if you ever look at a soccer ball, it's got both 5 membered and 6 membered fused rings together all over the whole thing. Stacked sheets is nothing more than graphite all over again. So you got nanotubes, buckyballs, they're all just different arrangements of carbon. And you've got diamonds, of course, as well. And there's been a lot of experimentation recently with not only graphene, but the different nanotubes and Buckminster fullerene and the different conformations you can make out of graphene sheets. rolling them up, twisting them, doing all kinds of things, maybe even rolling them up into multiple layers. And they have special electric or electronic properties. Graphene itself is a superconductor. It can transmit electrical current without any resistance at very, very cold temperatures. So it's a compound of very high, or substance of an extremely high, and it's not a compound, extremely high interest. It's an allotrope, meaning a form of carbon. Different elements can have different allotropes, or different compounds can have different allotropes. Basically just meaning it's the same formula, but just a different arrangement of the material. Here are some molecular solids. Now, unlike network covalent solids, molecular solids are independent little molecules. They are covalently bonded to each other. So these two iodines are covalently bonded to one another, but they are not covalently bonded to everything else. That's the difference. A network covalent compound has covalent bonds throughout the structure, but a molecular solid only has covalent bonds within the molecules. The molecules, however, are held together by intermolecular forces. So molecular solids tend to have low boiling points, especially if the molecules that make them up tend to be very, relatively small. If you can count the number of atoms on your hands, it's a small molecule. Low boiling. These, on the other hand, network covalent, tend to have extremely high boiling points, extremely high. They're comparable to ionic compounds. Think about it. When was the last time you saw a diamond melt? When was the last time you were able to take pencil lead and melt it? You can't. Extremely high melting points, and thus, well, if the melting point is high, the boiling point is going to be even higher, right? Boiling points are always higher than melting points. It takes more heat energy to boil something than it does to melt it. So network covalents have extremely high melting points and boiling points, but molecular solids have extremely low boiling points and low melting points and high vapor pressures. Relatively speaking, of course. So unlike network covalent molecules are discrete entities, these are discrete entities. Each one of these are individual carbon dioxides. The carbon dioxide, the C and the O's are bonded to each other by covalent bonds. But what bonds one carbon dioxide to another is not a covalent bond, but intermolecular forces bond these molecules together into this arrangement, into this molecular solid, this lattice structure. And it is a lattice structure. They do have a repeating array of carbon dioxide or iodine or whatever else. It looks like it's amorphous, but it's not. Finally, we get to metallic bonding, the sea of electrons. The sea of electrons is sitting on a bedrock of protons, or actually I should say even better, a bedrock of nuclei with a sea of electrons washing over it. Why is that? Metals come together and metals share their electrons, but not in the same way that covalent bonds do. Here you have metals share their electrons totally, absolutely, completely delocalized electrons. What does that mean? That means this metal, once it joins together with another metal, its electron can now freely flow anywhere throughout the entire metal's volume. In fact, that's what these little things represent here. An electron from one metal atom will follow a path anywhere, everywhere it wants to go. The electrons are totally free to move, and they move around randomly around the entire volume of the metal completely freely. This is why metals are good electrical conductors, because what is an electrical conductor? A free flow, or what's an electrical current? A free flow of electrons. Metals allow electrons to flow nearly completely freely. Now, so the electrons are just moving randomly. If we put a voltage, if we apply a voltage, a negative charge and a positive charge across the surface of the metal, like say, for example, we have a wire, a copper wire, in this case, a gold wire. If we apply a potential, meaning this side is negative and this side is positive, guess what? These random moving electrons, they're all going to go in one direction. They're all going to move away from the negative side and toward the positive side. That is a genuine electrical current. You don't really have a current until you get all the electrons moving in the same direction to one place. That's when you have an electrical current. You apply a voltage. This thing here represents voltage. Apply voltage. Actually, what this represents is kind of like a battery or a voltage source. You apply a voltage, which is just an electrical potential or like an electrical field. And the electrons will move in the direction of the positive side of that voltage, of that applied potential. Over here in this part, we have C. We have A, B, and C, by the way. So C represents heat. Another thing metals do, they conduct thermal energy. And we've talked about how metals have relatively low thermal conductivity, have low specific heat, so they're very good thermal conductors, low specific heat. The reason for that is as you add heat energy to one part of a metal, the electrons will actually find their way to flow away from the hotter part of the metal, taking the energy with them to the cooler parts of the metal. This is actually called conduction, but this is conduction of heat energy rather than electrical current, although it generates the same thing, it's flow of electrons. This is heat conduction, thermal energy conduction. One of the three ways to conduct heat is conduction. The other way is convection, and the other way is irradiation. So the electrons carry that energy that they've been given away from that part of the metal to the less energetic parts of the metal, thus conveying the heat from one part of the metal to another. This last one here is a little bit abstract. This isn't my picture, so I'm almost tempted to ignore this. The point they're making here, I've made this point before myself. I guess I'll make it again, but it's kind of a stupid picture to say this. What they're trying to represent here is that metals can deform without cracking or breaking. In other words, metals are malleable and they are ductile for the reason that because they're sharing all their electrons in common, they don't have to worry about suddenly being having like charges suddenly next to each other. Because the electrons are everywhere throughout the metal nuclei can also be pushed around rather flexibly. So metals are very tough. They're tough, but they're also bendable and flexible because the free flow of electrons allow those electrons to move wherever the nuclei move, thus neutralizing any kind of buildup of charge, so that two positive charges or two negative charges will never be right next to each other. There'll always be enough electrons to quickly move in and prevent too positive or too much of a buildup of positive charge to repel each other and explode. One of the problems with ionic compounds is if you try to bend an ionic compound, if you try to shear or bend an ionic compound, you will quickly move positive charges in close proximity to negative charges. You will disturb the ionic lattice, and you will end up pushing one layer that is positive next to another layer that is positive and negative, and they will repel and shatter. You don't want that. Metals don't have this problem because their electrons are not locked in place like ionic compounds. They are free to flow wherever they are needed to neutralize buildup of charge. That's what makes metals so flexible. And of course, that's what makes metals such good electrical and thermal conductors. So it's the sea of electrons picture of metals. Again, there are more complex and more, this is kind of a crude way of looking at it. It's okay for its level, but there are, you can delve into this forever. There's just no end to studying metals and the properties that they can exhibit. Okay, that is all there is for the intermolecular forces and the solid state. Oh, apparently it isn't. Here, one more example. I forgot about this, yeah. Okay, after this, that'll be it. And then we still have another part to this chapter. We'll talk about heating curves and the energetics of phase changes, heat of vaporization, heat of fusion. That's the next topic in module, what module is this? Whatever module this is. Module 12, I believe. So which of the following would have would have the highest vapor pressure at room temperature. The temperature doesn't really matter. It could be any temperature. The point is, at some given temperature, which one would you expect? As long as they're all at the same temperature, which one do you think will have the highest vapor pressure? High vapor pressure. By the way, this is not the answer. This here is just another molecule for you to look at. So we have an ionic compound. We have water, which is the most polar. It's got hydrogen, it's a molecule. It's one of the most polar molecules. It's hydrogen bonding. We have a hydrocarbon, which is London. We have mercury, which is metallic. Remember what we said about metallic. They are very tough and very strongly attracted to another, so strongly that mercury itself doesn't even want to touch anything else. It just wants to bind to its fellow mercury molecules. And then you got this thing, this monstrosity of a molecule, which clearly has hydrogen bonding. In addition to having dipole, in addition to having another hydrogen bonding section to it. So it's got two ends of hydrogen bonding, in addition to being relatively heavy. Right? I think this is the heaviest molecule on here. You've got 1, 2, 3, 4, 48 plus 32. You've got about 80, 94. Yeah, this is by far the heaviest molecule. Well, wait a minute. We got barium. Well, it's the heaviest molecule. It may not be the heaviest substance, but it is the heaviest molecule. Okay, so taking these one at a time, you've got a hydrogen bonding heavy molecule. This is definitely going to have a greater intermolecular force than water because it's got hydrogen bonding like water, but it's also got the benefit of high London dispersion force because it's also so heavy. Remember, when you're comparing like intermolecular forces, if you're comparing the same intermolecular forces, then you have to default to which one is heavier. You've got to fall back to, okay, well, they both have hydrogen bonding. Which one has the better London dispersion thing going for it? But what about ionic compounds? Ionic compounds have extremely high boiling points. What does that imply about their vapor pressure? Extremely low vapor pressure, right? Ionic compounds do not give off vapors. You've never smelled salt. Probably you've smelled salt water, but you've never smelled salt. In order for you to smell something, a part of that something, a particle of that something has to vaporize and enter your nose. I guarantee you've never smelled a metal and you've never smelled salt. And that brings me to the second point. Extremely low vapor pressure on mercury. Remember I mentioned that there's an extremely low vapor pressure in the vacuum of a barometer that holds mercury. But it's very, very low because mercury, being a metal, definitely has strong metallic bonds. Metallic bonds are beyond most other kinds of materials. So they are very tough to break and they are not going to vaporize very easily. Okay, so A and D are definitely out. Ionic and metallic are going to have a super high boiling points and they're going to have very low vapor pressures. They are not volatile materials at all. So that leaves us with hydrogen bonding, two hydrogen bonders, and a London. High vapor pressure goes with low intermolecular force. You're looking, by asking which one has the highest vapor pressure, you're looking for the lowest intermolecular force of attraction. That is going to be your medium-sized or your kind of small London dispersion force. And so that's C. The hydrogen bonders are both going to have higher vapor, lower vapor pressures, higher boiling points. And what else? I've got to admit, these are actually fairly close. And if we didn't already talk about it, this wouldn't be quite a fair question. Pentane does have a relatively high boiling point. It's getting close to water. I think it's around 70 or 80 degrees Celsius. So it's not that much further behind. But if you have to take a guess, and you're not given any other information, and the nonpolar molecule isn't so big, if you can count the number of, at least the number of carbons on one hand or on two hands at the most, chances are it's going to be a more volatile compound. So in this case, our answer is C, pentane, C5H12. Penta stands for 5 carbons, by the way, pentane. Okay, That is intermolecular forces and the solid state. We talked about the gaseous state. Now we talked about the solid state. We're going to talk about the energetics of different physical states and transforming between the different physical states in our next video, which is still for this module. We still haven't finished with this module. We're going to talk about the energetics of phase changes. And we're going to look at the heating curve and changing phase. And then we'll talk about some of the calculations related to that. And we're going to revisit the specific heat and heat capacity and Q equals M times C times delta T a little bit. And I hope you'll join me for that. I hope all of this has been informative and interesting for you, and I hope you have a better picture of what the atomic and molecular world looks like. Let me know if you have any questions or comments or concerns. I will see you in the next video. Take care all.